Hello and welcome to Video at Scale 2023. My name is Shinjan Tiwari and I support video processing infra at Meta. I have been associated with the field of large-scale video systems for almost 20 years. It's been so thrilling to see video grow so much. Be it learning to make your favorite dish, catching up on daily news, playing games with your friends, or streaming one to the fans. exchanging tidbits of life, or just relaxing and binging on your favorite content. Video is just everywhere. 65% of all internet traffic is now video or audio. And it continues to grow at 25% year over year. With advances in immersive displays, mixed reality, and a wand of generative AI in everybody's hand, I can only imagine that this growth is about to explode. How exciting! But creating an infra to support planet-scale media systems is not easy. Developers and architects must pay attention to finely balanced trade-offs. When to spend compute to save storage, and when to deploy a caching solution to fan out is every day's conversation when designing a system at this scale. Apart from system aspects, there is a deep signal processing vertical that must continue to make progress for us to meet the demand. Over the next 2 days, I would be your host, joining from Menlo Park in sunny California. Speakers join me from Bay Area, Bellevue, and across the world. I would take you on a journey of how large-scale systems are designed. What are some of the unique at-scale challenges that the industry is currently tackling? What works and what just stops to work as the order of traffic grows? How is the technology landscape changing from the point of view of media quality, devices, managing so much computation in real time for billions and billions of users across the world? What progress are we making in compression research? And how are we using data to drive optimal decisions in the ecosystem? How is generative AI disrupting the world of content creation and raising the bar of human creativity itself? With generative AI combined with video, we are looking at an unprecedented gap in compute and I/O infra. Feels like we are on a verge of solving the next set of at-scale challenges to sustain and satiate the demand of content. For this event, we will be joined by speakers from Eluvio, Google, Heygen, Ittiam, and Meta, where we will get a chance to dive deeply into some of the tech strands of what forms this formidable video infrastructure in the industry. Throughout the event, you will have an opportunity to chat with other attendees, as well as submit questions you have for our live Q&A sessions. Be sure to check out the event agenda on the AtScale conference website to learn more. As a reminder, all presentations and live Q&A sessions will be posted to the AtScale conference website, AtScale Facebook page, as well as the AtScale YouTube page following the event. Let's kick it off. I would like to introduce Michael Martinez, our keynote speaker. Michael is the engineering director who supports all of the video infra at Meta. Let's listen to him and learn how the landscape of this industry is ever changing and ever inspiring. Over to you, Michael.
Hello and welcome to Video at Scale 2023. I am excited to be here and kick things off today because I love video and technology, but more because I am a big believer in the At Scale series that brings together technologists from across industries. We share and we work through tough product, infra, reliability, and scale challenges. I'm Michael Martinez, and I lead the video infrastructure teams that support video experiences across Meta's family of products. And I am a longtime video nerd. Don't believe me? My journey started in video with tape-to-tape editing and big cameras. It was expensive and time-consuming to make and distribute quality content at that time. But after finishing school, I spent even more of my career building large-scale infrastructure and platforms to help ingest, process, deliver, and syndicate content globally. We did this over fiber, satellite, and wireless networks at this time. The software and the dedicated global infra required significant capital investments and often reserved only for the largest publishers and media companies. The next part of my 20-plus year career in video started when I joined Meta in 2016. It was in the early stages of what we now know as the explosion of social video adoption as people and businesses shifted from sharing pictures to video. The first At Scale event I attended was in 2017. It was Video at Scale hosted in the Bay Area. That year, Meta had several talks covering the early challenges that they had been overcoming in the social live broadcasting space. We also heard from many other companies talking about the approach to keeping up with the bandwidth needs to support the ever-growing amount of content that was shifting online as a result of media and publishing companies creating standalone offerings. Now, fast forward to today, video is absolutely everywhere. And the current preferred format, short form video, no surprise to all of us, Reels, TikToks, YouTube Shorts. Thanks to this bite-sized format, we are seeing new content creators, new content genres, new tools, and all of which is paired with AI-powered recommendations, linking us to discover new content, and ultimately is contributing to video being over 80% of the web traffic this year. Unbelievable. There is a lot at stake for these companies to get it right. Watching video is over half the time spent on Facebook and Instagram. 91% of businesses use video in their marketing, and we watch over 17 hours of video per week. People are 50% more likely to share video than any other type of content. I think in 2023 it is becoming clear as video products leverage AI, discovery, tools, and infra, that there's a flywheel emerging. Together, creators and viewers have a seamless product experience. And whether it's live events, shopping, gaming, movies, episodic content, or one of the many other content categories, there's something for everyone. This year, for me, as an example, edutainment content is my go-to. I am a DIYer, and I will use my own consumption habits from the year and the edutainment category to illustrate how important, powerful, and ultimately valuable connecting all the components together are for making a great experience. I am enjoying working on home projects, and like many, spend a lot of my time consuming content throughout my day and my week. Now, in the past, the intersection of these two interests, well, it crossed paths when I would put on HGTV in the living room and I'd watch the show and see rooms or houses transformed. The content was entertaining and often inspiring. However, I typically only watched it in the living room. And there was a big gap in the instructions that I needed to be successful in taking the inspiration from inspiration to reality. And when taking that to reality, I often had to turn to the internet to fill the gap in step-by-step instructions I needed to, because the TV show didn't have all of the steps and frankly wasn't accessible where the project was going on. This year, something wonderful happened for me. I opened up Facebook to catch up on my news feeds, who my friends and family are up to, caught up on a reel, and was being entertained. And shortly after selecting and watching a few reels, bam, the recommendation system kicked in, showing me just what I wanted to see. Stand-up comedy content. It made me laugh and it entertained me, but more so the educational content contractors were making helped me with my DIY project that I had just started. But even better, this bite-sized format enabled me to watch nearly anything, regardless of how much time I had. The comedy clips were made from long format shows. I may not have otherwise seen them. And the educational content from the contractor was broken down into short videos that showed each of the steps I needed to be successful in my project. Now, I think this can be characterized as a win-win-win. Content catalogs for the comic get new life as clips and may even build more of a following for that comic. The contractor with the educational videos can expand his brand while capturing himself doing a job he is already paid to do. The contractor is able to make compelling content thanks to the easy tools that are likely built into the app where he discovered content and is ultimately distributing. And he can build an audience thanks to the AI-powered recommendations that are able to connect people like me that have an interest and maybe even a problem to the content. The contractor is probably also excited and fulfilled because his work that normally isn't seen is now being highlighted. And maybe he also likes knowing and getting some satisfaction out of helping someone like me. As a viewer, I'm happy because I'm getting value out of the edutainment content the contractor is creating. But the next step, I think that this is the magic, because ads are being served. And again, because of the power of AI ads, they're smartly placed in the content and they're connected to what I'm consuming. I think all DIYers would admit that a well-placed ad for a local contractor, when you realize you aren't as handy and maybe in over your head, can really save a project. But more so, the ads. The contractor can participate in monetizing the content and now create a new revenue stream while not needing to take on any huge risks or even change jobs. And the cycle continues. When I am inspired from the content that I watched, and I post my own reel showing off the progress of my project and ultimately the completion after I call the contractor from the ad that I saw. Let's just say I'm hopeful that my creator journey will have more success than my short-lived tile career. Now, my journey in content this year is really to frame that there is a perfect overlay with the flywheel that I mentioned earlier. But more than that, I want to show and have you all imagine the voice that we can give to niche communities, entertainers, and enabling learning, and so much more. Of course, the content still remains king, but the tools, the infrastructure, they're all playing together to level the playing field. The content business isn't just for big companies with deep pockets anymore. It's now for everyone. As a further example, platforms like Instagram and Facebook offer free tools within the app to help make better, more compelling content for people. This is critical to helping folks create, publish, and generate more reach, and also maybe build a following. We still, of course, have APIs for professionals and creators and publishers and third parties. We want them to have an endpoint too, because their complex workflows also need a place. But under the hood, I think this is interesting. The UIs and the APIs, there's complex services, some of which we'll hear about today, but those complex software and infra powering video products allow real-time ingestion, job scheduling, processing, delivery around the world, all while simultaneously sending signal to ranking and integrity system. That allows people like us to come into an experience and get a compelling lineup of content. It meets my demand based on my time of day, interest, and so much more. The creator, the tools, and AI matching content and ads to people is amazingly powerful. But maintaining scale reliably billions of times a day to tie it all together is what keeps me passionate about the video infrastructure space and why the past 7 years at Meta have been some of the most exciting and fulfilling part of my career. Because the Meta video teams and really this community have been building product, software, and infra to enable anyone around the world to tell their story. This has leveled the playing field for who can create and share any format of video. Okay, we are not done. The future for all of us here today, it's bright. It's bright thanks to the challenges and exciting innovation ahead. Video, as mentioned earlier, is consuming over 80% of the world's internet traffic. And we need to continue to deliver high quality user experiences while thinking about the bandwidth. We need to save bandwidth. We need to reduce infrastructure costs for the network operator, for the creators, and the viewers. We can do it in a magnitude of ways, codecs, devices, hardware, but we also need to evolve video monetization beyond traditional advertising. We need to do this with updated subscription models, pay-per-view, merchandise sales, interactivity, and even virtual goods with inside the videos and live stream. We talked about short form video. As of late, we've really only been experimenting with the formats. We need to work on the capture devices as well. And we need to do this because our hands are full. Meta Ray-Ban Stories will help creators stay hands-free while giving an even better perspective to the viewer. Okay, of course, I can't leave out Gen AI because it holds the promise of enhanced realism, increased personalization, AI-driven video editing, accessibility improvements, cross-industry content generation, and AI-driven storytelling. Now, I could keep going on and on, but I am standing in the way of a fantastic lineup of speakers and presenters from Meta. We'll hear about their ever-evolving infrastructure to support video. From Google, we'll hear about RTMP enhancements and more. So I want to leave you with this. The video and social video landscape in 2023, it can be characterized by brevity, personalization, immersion, and commitment to making a positive impact on society. As content creators, brands, viewers, and engineers, we're part of an ever-evolving ecosystem where authenticity and engagement are paramount. To succeed in this dynamic landscape, remember, adapt to trends, move fast with flexibility, and most importantly, remember that reliability with seamless scale is the #1 feature people expect. Your ability to connect people and publishers in an authentic and meaningful way will be the driving force behind your work in the video space and ultimately the expansion of the video industry. Thank you. I wish you all an incredible year of innovation and creativity in the world of video.
Thank you, Michael, for setting up the larger context. Let's dive in now. Let's hear from Zainab Zahid from Meta. Zainab has been at Meta for over 8 years and works in videos to help build out Uma. Meta's unified media infra processing stack. Let's learn about what the unique challenges are in creating a processing infra at Meta, an infra that lies at the core of all media processing here. Over to you, Zainab.
Hello everyone, my name is Zainab Zahid. I'm an engineer at Meta, and today we are going to be diving into the Lambda service that powers all of the videos at Meta. Very specifically, we are going to be doing a case study on New Year's Eve. Now, New Year's Eve is the biggest day of the year for videos at Meta. Why is that? Well, let's think about what we're doing on December 31st. We're waiting for the fireworks to go off, and when that midnight strikes, we're going to pull out our phones, we're going to record those pretty fireworks, and maybe we're going to post an Instagram story, or maybe we're going to send that video over on Messenger, right? Now, let's kind of take a step back and think about that Lambda service that's powering all these videos. What does that look like? Now, on a regular day, we are executing billions of requests anyway. Now, you put in New Year's Eve and you put in that midnight, we're going to see a massive spike of traffic. The fun thing about this is every time zone is going to hit midnight at a different hour. So we're going to have an entire day of like pretty solidly spiky traffic. Now, it's not just the volume of the traffic that makes this a fun problem to solve and to talk about. It is the complexity and the diversity of all that traffic that we're serving on the same cluster and on the same tier. So you have a lot of use cases that are going to see a massive traffic spike that are co-located with use cases that are going to hold steady, right? Like if we think about ads are not going to spike with the fireworks, but your uploads are probably going to spike with the fireworks. We're also going to have use cases that are maybe very resource intensive. They're going to be very heavy use cases versus like very lightweight use cases. So our mission on New Year's Eve, our goal on New Year's Eve is to make sure that we are still giving the same customer experience and quality that everyone is used to. So very concretely, we're going to be looking at our reliability. We're going to be looking at our latency commitments, our latency requirements that customers have asked us for. And we're going to be looking at our compute. We are going to be looking at the efficiency and the utilization and throughput of our service and seeing that things are good. And of course, not to forget the engineers. We want to make sure that the engineers at Meta also have a nice day on New Year's Eve and nothing dies. So that's really the heart of this talk. I want to take a very holistic approach to talking about like, hey, what really shines about our system on New Year's Eve? So I am going to be diving into system-heavy design concepts of how do we design the system? What's really going to be helping us out and be critical to our success? So I'll talk about things like the queue and, how are we actually managing the ordering of our requests and why is that so special? I'm going to be talking about quotas. So how are we being smart about the resources we're using? How are we doing memoization and protecting ourselves? But like I said, I want to be holistic. I do also want to talk about the operational side of things. So this is testing. We can never just kind of write code and assume life is going to be okay. We need to actually test it and we need to make sure it's going to be okay. All right, so before we dive into it, I do want to start off with walking through the request lifecycle at a very high level, what's going on when you upload that video to fireworks. Okay, so Uma is going to go ahead and let's say we're getting a transcoding request. We want to generate an HD encoding for that fireworks video that you just uploaded. We're going to go ahead and get that request at the API level. It's a declarative API. You're just telling us you want some transcoding done. We're going to go ahead and take that request. We'll hit two data stores. The first one is we're going to hit a queue. So again, a queue is really going to help us manage the order of requests that we're processing. And then the second data store that we're going to go ahead and store this request in is, you can imagine, just a key value store. We want to be able to make sure that we are tracking the life cycle of this request. So this is our state tracking. Now, finally, when our resources are freeing up, our scheduler is going to be pulling off work from that queue and processing it. When all of that transcoding is done, we'll go ahead and send that request all the way back up. This is going to be an asynchronous callback. And that is a super high level request lifecycle. Okay. Now I want us to remember this diagram as much as possible. I will be talking about it a ton and I will also bring it back a ton and kind of point at it many times. Okay, so the first part we're going to dive into is the queue. Like I mentioned, the queue is that little pink box in the middle. We're using this queue to make sure that we are ordering our requests. Now, this is really, really critical in NYE because it decides who are we going to be prioritizing and how. Okay, so the queue is going to strongly pull in the requirements from what the customer is giving us. So very concretely, the customer is giving us a client ID. So we can think about this as an integer enum. You know, they're telling us who are they, who's the on-call. It's a very operational side of it. It's really critical. If something goes wrong, we need to know who to talk to. But more than that, the client ID will actually play a very special role. And we'll dive into that a little bit later. So we have our client ID, then we have our latency requirements. This is the customer telling us that, hey, this request is urgent. Like, you need to execute it ASAP. There's a user blocked on it. Or they might be like, hey, this request is optional. Like, it's really nice to have. If you have resources, I'll be happy if you execute it, right? So you have an entire spectrum. And then finally, the customer is also telling us the priority of the request. So we have a latency bucket, and then the customer is telling us that, hey, within this latency bucket, here's the priority of the request. So they're going to very concretely give us an integer that we're looking at. Okay, now, why is this important for the queue? Okay, so the first thing we're going to do, I mentioned client ID, super important. First thing we're going to do is each client ID is going to have its own topic when it comes to the queue. Some use cases are going to be very stable. They're not really going to see much more extra traffic because it's New Year's Eve. When we have a topic per client ID and we're doing round-robin DQs, that means your big guy, so in this case, our client ID A, can't really start the little guys. So we are going to be making sure that we are DQing work from everyone. Okay, so we've taken care of client ID. The next thing we're going to look at is the latency requirements and the priority, and how are they so critical. So we're going to go ahead and use the latency requirements and priority to order the items within our queue. So here we're saying, hey, the urgent requests, they're going to be at the first thing that we're DQing. And then within this latency category, this latency bucket of urgent requests, we're going to use the priorities that the customers are giving us and ordering the items within. Now, again, going back to the big picture, why is this important for New Year's Eve? I'm going to be asking that a lot. Why is this important for New Year's Eve? So once we're able to put together that latency requirement and that priority, we're able to be really smart about when we execute things. So we are able to time shift the compute to happen later if it's not necessary, right? So you imagine that spike of traffic coming in at midnight, you have a lot of urgent requests coming in, because imagine you have a lot of uploads coming in. A lot of users are waiting for their videos to go through. What are we gonna do? We have the latency requirement, we have the priorities. We can go ahead and prioritize everything that's urgent and everything that's deferrable, everything that's optional, everything that's low priority. We're gonna move it, we're gonna delay it. We're gonna wait until we have enough resources available, and we'll go ahead and execute that later. So that helps us be really smart about how we're managing our resources. All right, finally, we are going to be talking about one more thing when it comes to the queue, and I promise we can move on. The other thing that the queue is going to help us with is maintaining the reliability, okay? So New Year's Eve, what is the worst case scenario? The worst case scenario is you weren't ready for the spike and you got overloaded. Okay, that's the worst case scenario. So how does our queue step into it? We are able to monitor that, hey, this use case, traffic's not doing so well. We're seeing a whole bunch of failures. So now we're able to monitor the errors. We're able to kind of deduce if things are overloaded, if they need to be retried, if perhaps the errors are retriable, and we're able to put things back into the queue until we feel like things are recovering, okay? So the queue helps us retry, and it helps us delay and protect our downstream services if we think they might be getting overloaded, okay? So that's it for the queue. I feel like we have a pretty solid idea of where it's stepping in and why it's important in NYE. Now I'm gonna switch over and talk about quotas, okay? So going back to our favorite diagram of the day, we're gonna be looking at the scheduler piece. So again, I mentioned the scheduler is gonna be dequeuing work from the queue as soon as its resources are freeing up. So as soon as it thinks, hey, I have something I can execute, it'll go ahead and pull off a request. Now, the first thing it's going to do when it pulls off the request is, hey, do I have resources to actually run this guy? Do I have resources to actually execute? right? Now, yes, you could be, and that case is really not that interesting to talk about. So we're going to talk about the scenario where you don't have extra resources, right? Because remember, we said some of the use cases that we serve are really CPU intensive and some are not. Now imagine that CPU intensive use case spiked 10x on New Year's Eve. It's going to want a lot of resources, and others are going to be like, hey, we're good. We're matching our quota. We're not using too much of it. But this guy is going to go over its quota. So that's like the more interesting case. So what do we do? All right, so the first thing we're going to do is we're going to look at all these other neighbors that we have in our cluster. And we're going to be like, hey, do you have quota? Can I borrow some? You seem to be doing okay. Now let's say no one else has quota, okay? Everyone's spiked. Everyone has used their quota as much as possible. Like, what are we going to do? We're going to go ahead and we're going to look at how important is this request. Again, let's remember, we have our latency category and we have our priority to kind of make that decision. So let's say we have an urgent request. What are we going to do? We really need to run this request. That's our SLA. It needs to execute right away. The second option we're going to consider is preemption. Is there something less important that's running on the queue? Is there something that is not an urgent request? Okay, so that's where quotas are going to step in onto NYE. Is A, it's going to protect the little guys that are not using that much, that are like being very good citizens. And then it's also going to help us be friendly neighbors, and we're going to be able to help others that might be needing more resources than we have. Alrighty, the last bit thing we're going to dive into on the system side, and then I'll go into the testing and the operational side of New Year's Eve. So we're going to be talking about memoization. For this part of the concept, I want us to think about that state store that we talked about. So here I mentioned a request is coming in. We're going to be storing state about it. So for instance, hey, where is this request actually in the stack right now? Is it in the queue? Is it being executed? Has it been failing a lot? Are we on like the 4th retry for this request? If that makes sense, that's a lot of retries. So that's what the state store is. Now, this is where deduplication and memoization kicks in, right? So when we're dequeuing that request, before we're doing the quotas check, we're going to say, hey, have I seen you before? Do I already have the response that you're looking for? Maybe I just generated that transcode, that HD encoding that you were looking for. If we have it, we're going to return it to you. We're not going to be running duplicate work. Now, this one is really easy to follow, but it might not be intuitive. Why is this important on New Year's Eve? I want us to think about viral videos. I want us to think about videos becoming really popular at New Year's Eve, right? So at Meta, we have frameworks that we're going to call them view time frameworks, which are basically going to be monitoring videos in real time, and they're going to be looking at the watch time. And they're going to say, hey, this video is getting really popular. It's getting a lot of watch time. I want to go ahead and start making sure I have high quality lanes. So I'm going to kick off more transcoding requests. So when you put all of this together and you look at the lower level of the stack, which is where the Lambda service sits, that actually does result in duplicate requests. On New Year's Eve especially, we cannot be wasting resources running duplicate requests. So this guy right here, this state tracking, is really going to help protect us. Okay, now we're going to go into the operational side of things. Okay, now as I mentioned, just because we've written the code, we really can't assume it's going to work. So what are we going to do? We are going to test in production, okay? As crazy as that might sound, what we've learned over the years is it's really hard to put up a staging stack or a test stack that is truly the same as production. It's really easy to miss a config. It's really easy to, it's really hard to not be able to have the same capacity on your test or your staging stack. And in a lot of these times, like in this case especially, we want to be testing the scale. How are we going to do at that 10x spike, for example? So that scale and being able to replicate that in a staging stack is pretty hard to do. It's pretty expensive to do because you need capacity to do that. So what we're going to do is we're going to test in production. We're going to be very careful about it. We're going to have checks and balances in place. Our entire stack is going to know end to end that, hey, this request, that's a production request, but this request, that's a test request. If anything goes wrong, I know which request to drop and just completely shed that traffic. So we're going to be safe about it, but we're going to test in production. We want to know that production is actually ready for New Year's Eve. Okay, so very concretely, what we're going to do is we're going to generate test traffic. And we're going to go ahead and add that on to our production tier. We're going to add enough traffic so that we are hitting our NYE expected QPS load. And we're going to hold it. We're going to hold it for 15 to 30 minutes. Now, of course, when we're uploading fireworks, we don't actually do that for 15 to 30 minutes straight. But for our load test, we do want to test the worst case scenario. Worst case scenario is you hit your NYE spike right away, and then you just held it. Like, people were really excited. They just kept uploading those fireworks. Okay, and while we're at that peak and we're holding it for 15 to 30 minutes, we are going to be monitoring all the metrics that I mentioned earlier. So we are going to be monitoring what's the reliability at, what's the utilization of our pool? Are we being efficient about this? We are also going to be, of course, looking at the latency, right? We are replicating production traffic. So we have a very good assortment of urgent requests, deferrable requests, and optional requests. Are we doing the right thing? And then finally, I really like this diagram, so I have it one more time. But that pink box right there is our shadow framework. That's what I want to think about. We have a test framework that is sending test traffic through the exact same stack that IG is using or that Facebook is using. Again, the stack knows when it has a production request or a test request. And that's how we're protecting our customers while we test the stack, and we can shut it whenever. All right, that concludes us. So we talked about a ton of things, but I'm going to distill it down to just 2 takeaways. All right. So the first takeaway is expect the unexpected and be resilient. It sounds really generic, but it really reflects all of these design concepts that we've talked about. So for example, let's go back and think about memoization. In the perfect world, we shouldn't be getting duplicate requests. Why are we getting duplicate requests? What's going on? It doesn't matter. We're going to be ready for it. Let's kind of step back and think other than New Year's Eve. We're going to have other special days where videos are going to be critical to our users' experience. Okay, let's think about Lunar New Year. Let's think about the next World Cup or the next Super Bowl. These traffic spikes, we want to be ready for it. More importantly, we want to be ready for getting more traffic than we thought we would. How are we going to be resilient to that? And more importantly, to that second learning, how are we going to test and make sure that we are ready for that? And how are we going to see that in practice, that we are ready for it end to end? So the second learning that I hope we go away with is we're not too afraid to test in production. So 100%, we want to be careful. Our customers are P0. Their user experience is P0, but it's possible and really valuable to be testing in production. And that's about it. There you have it. So the next time you guys are uploading your fireworks on New Year's Eve, you know what's going on in the background.
Thank you, Zainab, for so many details and nuances about UMA's architecture. Up next, I would like to introduce Jitin and Mohnish. Jitin and Mohnish are software engineers in the video infrastructure org. They in particular pay special attention to the evolution of video infra components, an infra that stays a step ahead of the scale demand for processing and delivery. Over to you, folks.
Hello, everyone. I am Mohnish Penta, a software engineer at Video Infra here at Meta. Today, on behalf of Video Infra, my partner Jitin Thomas and I are excited to talk about the growth and evolution of Meta's VOD backend infrastructure that supports processing and delivery. We will share our journey over the past few years, during which we re-architected the backend to transition from an app-specific vertical stack to a shared horizontal stack that is currently adopted across Meta's apps like Facebook, Instagram, Messenger, Workplace, and Oculus. The defragmentation of our backend has significantly improved our resource efficiency and developer productivity. Let's take a quick look at our agenda. The talk is divided into 4 sections. In order to get a better sense of how it all started and how we got here, we'll start with discussing the growth of Meta's video ecosystem. Then we'll talk about the challenges that the growth brought us in scaling the video backend. Then we'll dive deeper into all the work that the team has done over the past few years to address some of these challenges. And then we'll finally conclude discussing all the wins and improvements that this work helped us get. So without spending much time, let's get right into it. But before we get into the details of growth and evolution, let's understand the scale of the platform. Meta's video backend currently powers some of the largest and the most popular social video apps by engagement and scale on the planet. Now, with that into perspective, let's try and see how we got here. The timeline gives us a sneak preview of some of the launches and milestones that we have seen over the years. It marks some of the key events since the launch of Facebook and Messenger video platform, acquisition of Instagram and Oculus, and launches of popular products like Reels and Stories. Now, let's get into specific details and see how the video backend evolved during this time. The slide here is discussing and talking about a snapshot of different areas that were evolved. Let's start with apps. As you must have noticed, there were some incremental changes that happened in this area over the past few years. At the company level, Facebook video platform started in-house, native to the app. Instagram and Oculus were acquired and evolved separately. Messenger also evolved as a separate platform. On the product side, social video landscape has evolved at one of its fastest pace in the past decade, witnessing rapid adoption and pushing the video uploads and views higher. Lastly, there was a lot of progress happening in the space of video compression technology. We went from H.264 to VP9 to AV1 currently. At the same time, audio quality had quite a few enhancements too. While the progress and the growth was amazing, there were some key areas that started coming up, which posed challenges in scaling the backend. Let's take a look at what these challenges were. Number one challenge that we saw was fragmentation in the backend infrastructure. The second challenge was need for cross-posting across Meta's apps. And the third was scaling efficiently as our backend grew. Let's take a look at each of these challenges in a little more detail. Let's start with the first challenge, fragmented backend infrastructure. As we have seen on the evolution timeline earlier, multiple video processing stacks emerged within the company and were evolving in silos with a lot of features that were common but developed more than once. While this was fine in the early days, as it helped apps bootstrap quickly and launch features, things quickly became tricky as new products were launched and video features became more advanced. Typically, our video backend stack comprises of 4 to 5 different core components like processing, data model, delivery, experimentation, and resource management. As we see in this picture, with time, the stacks evolved more vertically with very less sharing. In fact, achieving sharing in this setup was very difficult. This led to some of the following issues. First was higher cost to replicate the same feature across the stack. For example, putting VP9 in products needed a lot of rework rather than having a unified strategy. Second, the duplication led to a lot of maintenance overhead, gradually trickling down to code surfacing as site incidents. Developer productivity was not great. Developers spent a lot of time navigating across stacks and ramping up new engineer was difficult. Combination of all led to slower pace of development and launch of new features and products. Most importantly, all of this was going in the opposite direction of one of Meta's core principles of move fast. The second challenge that we were facing was need for more video cross-posting across Meta's apps. In a nutshell, as video products like Reels and Stories became more cross-app, the need for video cross-posting became a default requirement. It helped creators upload once and share it across apps to get better reach. While this was a great functionality for our customers, the fragmented infrastructure made things a lot tricky and complex. Weighing the pros and cons and the options available back then, the team decided to cater to the requirement by re-uploading and reprocessing videos to the respective apps each time users decided to share. While it helped solve the problem at hand and launch, but as growth caught up, things quickly became tricky. It started amplifying some of the core issues. Number one was duplicate compute and storage. Second, higher latency. While these were the issues manifesting from the very fact that each time a share happened, we re-uploaded and reprocessed the videos. The third important issue here was inconsistent playback experience. We saw issues around video quality each time a video was cross-posted to a different app. Now, as discussed earlier, video tech was evolving in silos. So were the compression technologies. What this meant was there was a difference in encoding settings and the compression tech across every app. This was an issue that was highlighted to us by our creators, since this started affecting their engagement. The third issue, and one of the important ones, the team realized that we needed efficient resource utilization. As we discussed earlier, in the last few years, we have witnessed the fastest pace of development in the social video landscape. The innovations have made its way to higher UGC, pushing the rate of organic growth higher. While at the same time, the compute and storage saw limited growth and did not grow at the same rate. The delta was pretty big. Well, the third important aspect that the team realized was learning the video watch patterns. We started seeing skew in the watch time distribution. What we found out was typically 1/3 of the videos were essentially responsible for most of the watch time on the platform. Now, these three factors made it evident that we need to think from ground up rather than addressing the issues with efficiency in silos. To summarize, with all the growth now that we were witnessing, there were these 6 main areas where inefficiencies escalated to bottlenecks and eventually became the main drivers to making re-architecture a necessity rather than a good to have. The team identified that the issues were related and had a common theme, as we discussed in the prior slides. This pushed the need for a holistic solution to be thought from the ground up. Now, at this point, I would like to invite my partner Jitin Thomas, who will discuss all the work that the team has done in the past few years to address some of these challenges. Jitin, over to you.
All right. Thank you, Mohanish. Hi, everyone. I'm Jitin. I'm from Video Infra here at Meta. I've been building and modernizing the VOD backend for Meta's platform. Now that we've seen the context of Meta's video ecosystem, the fragmented backend that supported it, and the challenges that we faced, let's take a look at how we address these. Our solution was composed of 2 parts. The first one was to unify our backend. This meant replacing the vertical app-specific silos that we had with horizontal services that could be shared by apps across Meta's platform. The second part was unifying the video data model. We replaced app-specific data models with an app-agnostic data model that could be shared across apps to represent videos and video-related artifacts. Let's dive deeper. On the left-hand side, you can see a diagram of what we had previously. As you've already seen, we had these app-specific silos which kind of replicated functions across them. This roughly included processing, delivery, experimentation, resource management, and data modeling. We replaced these vertical stacks with horizontal services that could be shared by apps all across Meta. At the bottom, you'll see the unified processing service. This exposes functions such as transcoding or compression, media composition or server-side editing, thumbnail extraction, encryption for DRM, and a host of other functions. The outputs of this processing service are then stored in a unified data model schema. And above this, we've built higher level services such as delivery, experimentation, and resource management that can be shared by all apps. Now, different apps plug into these shared services by specifying their policies as configurations. Let's dive a little deeper into this. So here's an overview of the control flow of a video throughout its lifecycle within Meta's platform. The first stage in the lifecycle of a video is, of course, upload. The client starts transferring the media bytes to our backend blob storage through a service called upload service. Once the transfer is done, the next step is for the client to make a graphical call to an upload endpoint. The next stage is media inspection. This is where we examine the uploaded media, verify that it's not malicious, and extract key properties of the media, such as bitrate, codec, resolution, duration, and other attributes. This information is then later used by apps to determine the best set of encodings to generate for that particular video. Once inspection is done, the next stage is running a set of upload processing pipelines. These pipelines were expressed as DAGs of operations. Each node in the DAG represents a task. This could include compression, thumbnail extraction, packaging, and so on. The edges between these nodes represent sequential dependencies. The DAGs themselves are run by a DAG processing service. And each node in the DAG could leverage our Lambda service, which is a priority-aware serverless compute farm that runs these jobs at scale. The outputs of these nodes and tasks are then stored in app-specific data models. This includes encodings and thumbnails. Once the processing is complete, the video is now ready for playback and can be published. When a video needs to be viewed by a viewer, the playback client, makes a call to our delivery GraphQL endpoint. This is to generate a .xml manifest that it can then use for dash playback. On the delivery side, we have app-specific logic to examine the encodings available for a video and filter out the most optimal set based on the viewer's device characteristics, network conditions, and a host of other factors. Once again, this logic is app-specific. Besides playback and upload, we also have a host of other backend services that tune and optimize our resource usage. This includes ROI-driven processing, which attempts to generate more advanced encodings with better compression efficiency for videos that have better engagement. We also have storage optimization jobs that aim to reduce our storage footprint without degrading user experience. Now let's compare this to the unified video backend. The key difference to note here is that we've replaced all of those app-specific functions or monolithic pipelines with a shared backend. The app-specific portions have now been reduced to very thin clients and snippets of configuration that express app policies. On the upload side, we still have the client using upload service to transfer the bytes to our backend blob storage. And after inspection, we send a callback to app-specific clients to now process the incoming upload. The clients then leverage the shared processing service to generate the necessary encodings, thumbnails, and to do server-side editing and packaging and a host of other functions to make the video ready for playback. The shared processing service itself is composed of three services under the hood. One is the data model service. This is the one that mutates and stores artifacts in our unified data model. Then we have a media transform service, which is a workflow system that exposes functions to compress videos to extract thumbnails and a host of other things. And then we have the Lambda service, which, as I mentioned, is a priority-aware serverless compute farm to run these jobs at scale. At playback time, the client again makes a call to a delivery GraphQL endpoint. And this time, instead of using app-specific logic, we leverage the unified video delivery service to generate the dash manifest for playback. In a similar vein, we've also unified our ROI-driven processing systems and storage compaction services. Now, to summarize, we had these functions at varying levels of sophistication across apps prior to the unification. But with this move, we not only defragment our infrastructure, we're also able to expose the cutting-edge technology we have in every one of these functions to every app within Meta. We build once and ship all the time. Let's take a look at the data model side of things as well. At Meta, entities are represented as nodes within our social graph store. So let's consider the example of a story video that is cross-posted from Facebook to Instagram. Now within this graph store, we also have a concept called universes. These universes separate nodes into logical partitions to ensure isolation of data and schemas and policies. In this diagram, the blue nodes represent the Facebook story. As you can see, there's a node for the user, for the story, for the video, and for the artifacts of that video, including thumbnails and encodings. Now, when the video is cross-posted from Facebook to Instagram, although we already have thumbnails and encodings ready, we have no way of reusing them on the Instagram side. This is because nodes that belong to two different universes are incompatible with each other. They cannot have edges between them. This meant that on cross-posting, we had to reprocess the video on Instagram side. This resulted in higher latency. It increases chances of failure, which means lower reliability. And we also have to duplicate our compute and storage processes and waste resources. How did we address them? We took advantage of another feature within our graph store called the shared multiverse. Nodes in the multiverse are different in that they can have edges from nodes that belong to other universes. Let's take a look at the same example of a story video cross-posted from Facebook to Instagram. In this case, we still have the parent nodes, user, story, and video, that belong to the Facebook universe. But what's different here? The artifacts that we generate through the unified processing service are now stored in a shared multiverse, and the Facebook node takes a link to the shared asset. In this case, cross-posting becomes a lot easier. We don't have to reprocess the video on the Instagram side, but rather we could do a copy by reference. All we have to do is add a link from the Instagram side to the shared asset. This reduces latency of cross-posting, increases reliability, and we also don't have to duplicate compute and storage resource usage. Now I would like to invite my friend Monish back to walk us through some of the key wins that we unblocked from this migration. Monish, over to you.
All right. Thanks a lot, Jitin, for the deep dive and sharing all the work that the team has done over the past few years. The new infra has inbuilt support for seamless video cross-posting, addressing most of the issues that we have seen earlier. Along with common API and standardization across services, it has also promoted common tooling, which in turn has boosted developer productivity and helped faster onboarding. The work around ROI-driven view time encode processing has greatly helped in streamlining the resource utilization. And the list goes on. Briefly, but I would like to also mention the new avenues that the work has helped open up, like centralized resource attribution and management. Now, before we conclude, we would love to share some of the key wins that this work has helped us achieve. Number one, resource wins. We were able to achieve around 50% reduction in the compute and storage spent in videos that were cross-posted. On the user experience side, we were able to reduce the cross-posting latency by approximately 50%. Talking about time to market and developer productivity wins, we were able to achieve around 60% of reduction in the development and the experimentation lifecycle of launching a new feature, And lastly, for better systems, we were able to reduce the code and configuration by around 80%, delivering the same functionality. Well, at this point, this marks the end of this talk. On behalf of Jitin and Video Infra, we would love to thank each one of you for taking time to attend this session. Have a great rest of your day. Thank you.
Thank you so much, Jitin and Monish. It's incredible to learn how multiple business priorities can weigh heavily on infra. Now I will hand it off to Mike Starr from Meta. Mike is a long-term Meta employee and has helped build and scale data and video systems. A large-scale system designed for media cannot be built without understanding the nuances of a media file. Let's learn from Mike the secret sauce. After Mike's presentation, we will have a live Q&A session with the speakers we have heard so far. So folks, keep letting those questions come in through the chat box at the @Scale website. We will address it right away. Please take it over, Mike.
Hey everyone, my name is Mike Starr, and today I'm going to talk about virtual video files. This is a technique we use at Meta to seamlessly slice, dice, split, and combine billions of videos per day. Working at Meta presents a challenge of supporting a diverse array of video products, from short-form reels and direct messaging all the way up to long-form live streaming and high-resolution Oculus content. We have to deal with a wide range of products and use cases. Because of this, I create tools and abstractions to simplify the processing of video content. Today, I'll delve into a few of these tools, starting with the concept of a virtual video file. So what exactly is a virtual video file? Imagine being able to select any set of frames from any video and instantly have access to a new video file with just those frames. Or better yet, imagine combining samples from multiple files into one single file instantaneously. This is the essence of a virtual video file. The ability to select samples from various sources and create a new video file containing exactly the data that you need instantly. Now the catch here is that I'm lying. What you get immediately is not an actual file, but a representation of the file. You can ask how big the file is, you can read any range of bytes from the file, but the file does not actually exist anywhere. Instead, every aspect of materializing this data and computing this file is done lazily. So in essence, these are virtual video files. They look and feel like real files, but they are only actually materialized upon request. So why did we build this? The short answer is storage costs. Let's take a quick journey through the history of videos at Meta. From our beginnings in 2007 to acquiring Instagram in 2012 and beyond, our video features have expanded, and so too have the amount of uploads to Facebook and Meta. But we had a problem. The storage costs were going up way faster than video uploads were, and we needed to do something about this. As it turns out, one of the biggest consumers of storage was progressive MP4s. These are files that we keep around for video players and devices that do not support dash playback. Now, while progressive gets less than 5% of the view time, it was costing us more than 10% in terms of physical storage costs. And hence, virtual video files were born. Rather than physically storing a separate copy of all of our progressive MP4s, we will create them on the fly using our dash sources and virtual video files. So here's what I'll cover today. First, we'll do a very quick crash course in MP4 files, just so that we understand the basics of what goes into the file format itself. Second, we'll look at how virtual video files are implemented and two of their practical applications. And finally, we'll look at how we integrate this technology at Meta with the world's most common encoder, FFmpeg. So very quickly, MP4 files. MP4 files are a video container or file format. A container brings organization to raw audio and video data. Containers hold both high-level information and metadata, like the number of tracks and their types, but perhaps more importantly, they also contain a data structure known as the sample table. The sample table contains the exact position, size, timestamp, and other key metadata about every frame within the video file itself. MP4 files organize the data in a tree-like structure. The file itself sits at the root, and then the nodes of the graph comprise the interior. The nodes of a graph in an MP4 file are typically called boxes or atoms. So the MDAT box, or movie data box, is just a blob containing all of the samples for either the audio or video tracks. Perhaps most importantly is the move or movie atom, which contains the movie metadata and all of the sample tables. Physically speaking, the children of any node are serialized within their parents, and so this is how we compact the actual tree-like structure into an on-disk format. And an important thing to note here is that the metadata atoms themselves actually only make up a very small portion of the overall file size. We'll come back to this in a few minutes. Now, not all MP4 files are created equal. In the real world, there are two main types that are often used. First, we have what are known as progressive MP4s. This is what you would typically have on your phone, your laptop, and it might be what you would serve a video file from an HTML page using a video tag. Progressive MP4 files typically contain both audio and video tracks together in a single file. And lastly, progressive MP4 files put the sample tables entirely within the move atom, and these have a global view of every sample within the file. By placing the sample tables in the move atom and the move atom at the front of the file, then your browser can download just a small, tiny portion of the video and then immediately be able to start playback. Now, the second common type of MP4 is known as a fragmented MP4. And this is typically what's used in dash playback for online video players. With a fragmented MP4, the sample table in the move atom is actually empty, and instead a two-level index scheme is used instead. Fragmented MP4s are broken into fragments of data, which might be 2 to 5 seconds each. An atom known as the SIDX, or segment index, contains the location of each of these fragments. And then each fragment begins with a MOOF, or movie fragment atom, which contains the location of just the local samples to that fragment. So in order to build the full sample table for a fragmented MP4, we first need to read the SIDX in order to locate the location of all of the fragments, and then we need to read the MOOF atoms in order to locate the samples within each fragment. Finally, we have what's known as remuxing. Remuxing is the process of converting from one video file format to another. Because we're not actually changing the underlying video or audio data, we're only changing the file structure itself, this process should be very fast and efficient. It's essentially a race to see how fast can you download and write the data. In reality, however, remuxing from dash to progressive runs into an interesting chicken and the egg problem. We want the move atom to be at the front of the file so that we can immediately start playing it back from our browser. But in order for the move atom to be at the front, we need to know the position of all of the samples within the file, which are after the move atom. But in order to know the position of those samples, we need to know how big is the move atom in the first place. In a naive implementation of a progressive muxer, the way you would work around this is to first write all of the samples to disk, keep track of their location, compute the move atom, and then we shuffle everything backwards so that we have space for the move atom at the front. However, this is terribly inefficient because we need to process the entire input and generate the entire output before any portion of the file is actually usable. This would clearly break down if we were trying to process a large multi-gigabyte file. And hence, this is where virtual video files come in. The concept of a virtual video file addresses the challenge of creating a progressive MP4 instantly from one or more sources without the need to actually generate the entire file. This approach not only solves our progressive storage problem, but as we'll see, unlocks and simplifies a bunch of other video processing applications too. So our goal is to implement a virtual file interface that allows us to know the size of the resultant MP4 and read data at any offset within the file. This involves creating a virtual representation of the output and then materializing the data as it's needed. Here's how we'll do that. So we begin by demuxing the source files, which is analyzing the source files, reading their sample tables, and converting this into an in-memory representation of the MP4 file. You can think of an MP4 file as a structure that has a list of tracks. Each track has metadata and a list of samples, and each sample contains its timestamp, offset, size, and whether or not it's a keyframe. An important thing to note is we'll also keep track of the file from which each sample came from so that we know how to later read the data if we're working with multiple input files. Next, we need to determine what would the sample offsets be if we were to produce the MP4. We'll start by sorting the samples in ascending order of decode timestamp so that our player can download and play back smoothly. And then we'll iterate over all of these sorted samples to determine what is their new position within an MDAT if they were to be interleaved together. With the samples laid out in the MDAT that we pretended to create, we'll now build our move atom using this layout. We can calculate what the resulting size of the move atom will be, and then adjust and account for this by adjusting the offsets of all of the samples in the MDAT, pretending that the move atom is actually at the front of the file now. And that's it. Finally, to materialize the file, we'll either do one of two things. If the read overlaps with our move atom, which is sitting in memory, we serve it out of memory directly. If the read overlaps with the MDAT atom, we'll determine what portion of which samples from which files needs to be read, and then we'll read that data directly from the sources where those samples should be coming from. That's it. We've devised a way to take samples from any number of sources and then lazily materialize a new MP4 with exactly those samples. One thing that's worth noting is that the move atom itself can be pre-computed by demuxing once and then caching this in memory. As I mentioned before, the move atom is only 1/100th of the size of the file, and so this is fairly cheap to cache not only in memory or even in a database. We also have the ability to serve read requests instantaneously, regardless of the file size itself. This is handy because it means that even for really large files that might be multiple gigabytes, we don't actually need to go and process multiple gigabytes. We only fetch the data that's being accessed. And because we're doing this all lazily, we ultimately end up saving on I/O and disk resources and can serve things instantaneously. Now, while we initially came up with the idea of a virtual file to solve the storage problem of progressive MP4s, we realized that it can actually be used to greatly simplify other processes in handling video data too. From distributed encoding to converting live videos into static VOD, virtual video files give us a powerful way to address, manipulate, and change the layout of our video data efficiently. We're going to take a closer look at two of these examples. So the first use case, which motivated us to build the technology again, is serving progressive MP4 files to players that don't support Dash. To do this, we're going to take our existing Dash sources and produce a single progressive on the fly. What we'll do is we'll construct a virtual video file, which uses one of the Dash audio and video sources for a given piece of media. We'll send a URL to our players, which will map to an HTTP server that knows how to generate this virtual video file. The players can fetch the full content size using an HTTP head request, and will return the virtual file size. And then the players can also fetch the data within the file by using HTTP byte range requests. What this means is that we can serve multi-hour, multi-gigabyte content, but only actually have to fetch the data as it's being played back in real time. The result is that we only need to store Dash encodings, and we can save big on storage costs. The second use case we'll look at is distributed encoding. Now, distributed encoding is a technique used to break a large video into smaller chunks, transcode each of those in parallel, and then stitch the results back together. Distributed encoding is super easy to conceptualize. However, the devil is in the details. Splitting and stitching together segments accurately and efficiently turns out to be very tricky, especially if you want to avoid having any single point within your system that acts as a bottleneck and we have to write everything to disk. Imagine you have a really long video. First, what we can do is analyze the source and locate where we want to make our video into chunks. For each chunk, we can then use a virtual video file to address and refer just to the samples within that chunk. This allows a remote worker to download and materialize a file that only has that portion of data and only actually needs to read that portion of data, not the entire file. And finally, after we've transcoded each of these independent chunks, we need to stitch them back together. Virtual video files can also help us here. We'll create a new virtual video file that concatenates all of the results of all of our chunks, and then we can do a streaming read and write to our network file storage so that we never actually have to materialize this file on any one local disk. So with virtual video files, we have this really powerful abstraction to refer to media data, but how do we make that easy to use? How do we fit this into the broader ecosystem of FFmpeg, which is the Swiss Army knife of processing video? For years now at Meta, the answer has been a thing called fuse. So fuse gets its name from the Linux kernel fuse, or file system in user space. The idea is to be able to build a custom file protocol for FFmpeg and lets us develop this file protocol outside of FFmpeg source code itself. You can think of the FFmpeg code as being the kernel then in this analogy, and then our own C++ code as being the user space component. How this works is that we have a stable, unchanging protocol in FFmpeg, which simply dynamically loads a shared object and proxies the reads, writes, seeks, and closes to our handler in the shared object. And much like Fuse proper, what this allows us to do is quickly iterate on the file protocols themselves and release them at a different cadence than FFmpeg itself. And on top of that, we can use whatever programming language we want. So when FFmpeg sees the fuse protocol for an input or an output, it will dynamically load our shared object fuse.so. All of the file objects operations coming from FFmpeg will then be proxied through this shared object to our C++ handler code. And then with this, we can directly connect not only FFmpeg to our internal data stores at Meta, but we can also connect it to virtual video files as described in the first part of the talk. So for example, we could leverage the fuse connector to read our source file, but only use a subset of the frames using a virtual video file. This connector will then load up our logic for downloading just those samples. And then on the output path, we'll write directly to our blob storage and avoid having to write to local disk. Fuse does this by supporting nested protocols. so that we can build and deploy one single shared object that actually has connectors for a variety of different output types and backends. At this point, then, you might be wondering, why not just use regular Fuse? So Fuse is a very interesting beast. On the one hand, it offers an attractively powerful and flexible way of thinking about files and moving data around. On the other hand, when things go wrong, they can go spectacularly wrong. And for a long time now, I've mostly bounced around and sat on the middle of this curve, loving Fuse for its simplicity and robust, easy ease of use. However, in recent years, we've finally started to shift to the right-hand side and embracing Fuse as a way to replace Fuse. So how does Fuse stack up against Fuse? I'll start by going over the cons. And the biggest one is initial upfront developer costs are much, much higher. Because Fuse, you're basically building and implementing a POSIX API, your users and your code will assume that your file system will do the right thing. And if it doesn't, it will fail in really, really bad ways. And in this case, errors are actually your best case failures. Worst case, you'll get indefinite hangs, corrupt data, poor quality of service, or spend hours debugging and scratching your head. Lastly, because everything is indirectly going through the file system, it means our tight integration with FFmpeg is lost, and it's harder to signal errors, timeouts, and that sort of thing. However, if you do pay all of these steep upfront costs and achieve a stable state of nirvana and have some sort of working Fuse file system, then the pros can start to shine. First and foremost, Fuse can be used by anything, not just FFmpeg. This means that other tools, services, and even non-video use cases can easily access not only our blob stores, but also virtual video files. Another huge benefit is being able to use the kernel page cache. With this, you can effectively use the entire available system memory and never really have to worry about because you have too much cached data. And finally, perhaps most importantly, this triggers a shift in the way that you think about files. And really, we embrace the unique philosophy that everything is a file. We can access our blob store directly, and we can even access subsets of samples within videos, just like a regular file. And by doing this, it really simplifies a lot of other pieces in our architectures. So to recap, we've talked about virtual MP4 files. These are an abstraction born out of the necessity of saving storage, but which have actually opened up and simplified a bunch of other use cases in video like distributed encoding and live to VOD. We've talked about various ways of getting data in and out of FFmpeg, from Fuse, which is tightly coupled to the FFmpeg ecosystem itself, all the way to full-blown Fuse file system, which can work with anything. And what I hope you take away from this talk is this. Investing in the right tools and APIs can allow you to hide complexity behind simple abstractions and then take on more problems faster and with a smile on your face. Thank you.
Hi, everyone. Welcome to the first Q&A session for Video at Scale. Thank you, Mike, Zainab, Monish, and Jitin for your talks. I think even though I worked at Video Infra with you guys for a long time, there were a lot of things that I didn't realize, I didn't know until I listened to those talks. So thank you for them. Let's jump into the first questions that we see now. The first question is for Jitin and Monish, whoever wants to pick it up. The first question is, different apps could have different requirements on Dash or HLS manifest. For example, one app or use case may only want higher or lower renditions. Do we generate them beforehand or on demand? Or do we use a shared Dash or HLS manifest but rely on the players to decide?
Thank you, Tia. I can take that question. Firstly, that's a great question to start the discussion. Short answer, no, we do not generate every manifest beforehand, because for the reason you mentioned, things change. Every app, every product, like every app like Instagram, Facebook, every product within that has different requirements which dynamically change. So on the back end, we have a dynamic manifest generation service. what the service ensures is based on the real-time requirement that the app or the player is telling us. We in real time will put together all the different permutation combinations which suit the best for the current user who is trying to watch the video, and stitch together the manifest and deliver it to the user.
Got it. Thank you. The next question is for Mike. So how long does it take for us to compute the move atom for a large video?
Thanks, yeah. Yeah, it's a great question. So the video duration is actually the biggest factor for how long it takes to demux a video, as opposed to the video size. If you have a high bitrate video that's 10 gigabytes, but it's only 30 seconds long, then the actual metadata about the video is fairly sparse throughout the video, and then the video data is like the large portion of the size. If you take over like a 4-hour live video where every 5 seconds you have a move atom, those are the ones that are actually like hard to demux because you have to do a bunch of really small reads across the entire file. And so those are the ones that actually take the longest, and that might still finish within like a second though, because you basically are fetching a very small portion of a lot of different byte ranges of the file. So yeah, the long answer short is that we can do pretty much every video in like less than a second.
Okay, that's good to know. The next question, or I guess it's a statement during Mike's talk, but I wonder if you have any comments on it. The statement is, FFmpeg, OpenSSL, and HTTP Connect already handles this through byte range calls.
Yeah, no, it's a good observation. So I know I've seen posts where people, to connect to say like Amazon S3, for example, you use S3's CLI to get the HTTPS URL, and then you can use HTTP chunk transfer and range requests to actually like slice into the bytes. However, the pro of FUs still is that we get a lot of lower level control over how FFmpeg's reads, which tend to be like really small byte range reads, maybe only a couple bytes at a time. We can control how those actually map to backend reads against our blob store. So if FFmpeg accesses maybe only 5 or 10 bytes, we can translate to that to the optimal read size for our backend, which might be 8 megabytes. And then we can also do read ahead caching and stuff like that. And then when it comes to streaming, so streaming inputs or outputs to FFmpeg, same thing. You get a little bit more control when you're connecting FFmpeg like directly to the client of your blob store, as opposed to having to like coerce everything to fit into HTTP chunk transfer, be it for upload or download. So we did definitely consider HTTP connector, and it's definitely useful and easy because it works out of the box. But when you really want to have like fine level control, it's nice to be able to directly map any FFmpeg IO operation to how you actually want that translated to the backend.
Got it. Thank you. The next question is for the floor. So whoever wants to take it. The question is, I am curious how you measure the efficiency of infrastructure cost savings because we are running our own data center.
I think probably each one of us can add to this. I can start with it. So yeah, that's a pretty in-depth question. So the short answer is there isn't one specific metric that measures the efficiency or saving of the entire infrastructure. So on a high level, the team has come up with separate metrics to measure the efficiency and in terms of compute. For example, when you're talking about the delivery stack or encode processing stack, then when it comes to storing the videos, we are looking at storage as a metric. When you're looking at user experience as one of the metrics, then on the right side we're looking at latency. On the viewer side, we are looking at video quality, MOS, and a bunch of other metrics. So in a nutshell, there's a combination of multiple metrics that work in tandem. The end goal is, of course, to give the best user experience. But then for delivering that best user experience, how do we tweak each and every metric to make sure that we are doing this optimally? And
if at all we see leaks in any of the metrics, the separation of the current stack or the architecture or the framework of metrics will help us decide what is the aspect that we need to go tune by making sure that the user experience is not regressed. I would stop there. Any other thoughts, please?
Anyone else have anything to add to that?
So for when we talk about efficiency, right, we basically think about compute and storage, right? With compute, we have a finite amount of compute, and the model that like Zainab described is we basically try to do the most we can with whatever the compute is. And as the day goes through, there are like peaks and troughs where we get a lot of uploads, and then at nighttime when people are sleeping, there's less traffic. And so we try to use that off-peak time to like fill in the gaps and improve quality. So that's like the model on compute. And then storage, again, it's like there's the stuff you have to store permanently, and then we try to also make the best encoding possible, like while the video is actively being watched, and then try to clean up when the video is not popular anymore.
Yeah, and to add to what Monish mentioned, there's also work going on to see if we could build a uniform normalized metric that could capture all of these different dimensions across compute, storage, and even egress. That's still a work in progress, but yeah, at the moment, it's a collection of different metrics that we monitor to ensure that we're making best use of the resources that we have, and we also don't regress the experience that our users get.
Got it. Yeah, that's a great point, and it's a really good question. I think it's a very complicated issue here, but I guess as Jitin said, it makes sense to simplify it. So the next question that we have is for Zainab. So Zainab, you mentioned expect the unexpected in learnings. So looking at the history of New Year's Eve at Meta, has your team ever been taken by a surprise or observed unexpected behavior during the event? And if so, how did you learn from it?
That's a good question. So the first part of my answer is going to be boring because I think Uma's a new service. We've been around for about 2 years or so. New Year's Eve at Uma has actually been really boring. It's been actually quite silent. And that's because testing has been really exciting. We've kind of front-loaded all the issues that we could have seen on New Year's Eve prior to that. So I can talk about like the more exciting issues that were hit during testing, which meant that we had a boring New Year's Eve. I think one of the really nice benefits of load testing is it is the best way to verify capacity. So did you actually turn up enough capacity to be able to take the load that you're expecting? When you're running a load test, you'll very quickly see that, oh, hey, this service or this region is running really hot. And it gives you a chance to kind of take a step back and redo that whole exercise. Load testing is also a really fun way to find out you have bad configurations. So you might realize that, hey, I drained that region when I was on call last week, and like I forgot to undrain it. That region is completely idle. I'm load testing the service, and like that region's not doing anything. So interesting configuration issues that we'll find. I think another fun one that we find are retry storms. So when you are load testing, you are more likely to hit error paths, so things going wrong. So you have a really nice check on, hey, what are the retry policies on this path? Are we seeing that with every hop, we're multiplying the retries? And is that how it really should be happening? So I think those are like the more exciting things that we found during testing.
Well, it's good that we catch them during testing and not during New Year's Eve. Thank you. There's one more question I see for Mike. So it says virtual file is very similar to QuickTime reference technology. Was that a consideration when you were developing virtual files?
Yeah, so like QuickTime reference and also just like the MP4 spec itself does have a lot of like interesting features built in to support similar ideas. Like you can have an MP4 file where the data is like a reference to some other file. And so in that sense, yes, it's like very similar conceptually. Probably the only real difference between what this is doing and QuickTime's reference files is in the implementation itself, right? Again, because we're really concerned about being able to serve these files in low latency, the main difference is like we want to be able to go from a dash file to having sort of like the equivalent of the QuickTime reference file. And we want to do that without having to download the entire source file. And so ultimately, it's really just about tooling, right? You want to make the tool to go from two dash sources like audio video to having your like reference file or your move atom or your virtual video file, whatever you want to call it. You want to be able to do that with like minimum latency, minimum bytes read, because at the end of the day, we have like a user or someone out there waiting to watch this video, and so it needs to be fast. But yeah, there's a lot of overlap in the tech, and conceptually they're basically the same thing. Yeah.
Got it. Awesome. Thank you. The next question is for Monish. So you were talking about the video shared infrastructure. In this world, how does your team decide how to prioritize traffic across the multitude of apps?
Right. So, one of the guiding principles of the shared infrastructure was, as we were trying to solve the problem of defragmentation, moving from a vertical stack model to a horizontal stack model, one of the main guiding principle that we made sure was tenant isolation, which is end-to-end vertical tenant isolation, right? From the moment the request enters the data center all the way down to, if it's processing a video upload or when it comes to delivery. Now, given this inherent capability that we have built, there is prioritization that is happening on two fronts. First is the end app, like for example, Facebook Messenger, they pretty much have control of everything that they drive from the products. This is tweaked through configs, and they control the capacity. The second is diving a bit deeper into capacity is about prioritization within a specific app. For example, Facebook or Messenger or Instagram will have X number of video uploads. Now, amongst these video uploads, again, each of the app have the required controls or the configuration to decide the prioritization. As you saw in the talk already, the view time encoding component that we have, that is something that each app controls in a tenant isolated way. They decide what heuristics that they want to use to essentially prioritize which videos should be processed with what encoding, which videos should be processed over other videos, and things like that. So combining both these models together, end of the day, the app has full control on what gets processed, when it gets processed, and if they want to change it, they can change it based on their needs. And lastly, to conclude, all of this, the capacity tuning from the compute pools down to the storage pools also is completely tunable and owned by each and every app.
I see. Yeah, that sounds like a good way to avoid noisy neighbor. So even like Messenger has to bring their own capacity to prevent them from using Facebook capacity and affecting their traffic.
Exactly. So pretty much Messenger, Facebook, they are all operating as tenants on the shared infrastructure at this point.
Thank you. The next question is for Jitin. So I think I can attest to how challenging it was to actually move to this stack. What were the challenges specifically the team faced in migrating the production traffic to the new infrastructure while ensuring that the user experience was not affected?
Yeah, that's a great question. This whole project took, I think, about 3 years from start to finish. And one of the first challenges we had was looking at the existing infrastructure, all the different pipelines and logic that had been built over several years, and distilling that into APIs and features that were not duplicated and also were extensible and provided a solid foundation to build on top of. So just looking at the existing system and breaking it down into what it would look like in the new world, and that it satisfies our requirements of extensibility and decoupling and so on. That I think was a major challenge. We had multiple rounds of design discussions, brainstorming sessions, and it continued throughout the lifecycle of the project as we tackled every single feature. I would say that of all the stages, probably implementation was the easier one, because once we knew what we needed to build, we just went and built it. The next big challenge was actually migration, because we couldn't just bring down the whole system and then reboot it at some point, right? So we had to keep the system running. Users should not have any regressions in either creator experience or playback experience. and we couldn't regress our the storage and compute efficiency wins that we unlocked over the years. So migrating the whole thing while keeping the system running and validating that every single point is at parity. And this includes upload time, creation, reliability, and latency. It includes playback quality, storage and compute efficiency, and a host of other metrics. So it is almost like you have a bunch of buildings with their own foundations, and you sort of keep the buildings intact, remove all the foundations, and put a new foundation that covers all of these. It is kind of like that. So yeah, just maintaining the whole thing, keeping the lights on, and at the same time shifting this under the hood. That was a massive challenge, and it took a bunch of teams and engineers, everyone over here, to actually get it done successfully. So a lot of interesting learnings and experiences that came out of that exercise.
Yeah, 3 years sounds like a very long time for sure. Like, is that something you guys anticipated when you guys decided to embark on it? Or was it like a lot of unexpected obstacles that made it take 3 years to finish?
I think it was, I don't think we really discussed the 3 year. We had a roadmap somewhere to the midpoint. Like, we knew the next couple of big milestones we wanted to hit. And once we hit those, the subsequent milestones just got unlocked. So I don't think we looked at it as an entire roadmap from the start. Like, we had some vague idea of where we wanted to be, but we just took it like a couple of milestones at a time. And yeah,
I feel like it was the last 20% was the longest and hardest. It always is. It was easy to get most videos moved over, but not everything. And then the last 20% took forever.
You saved the hardest part for last, I guess. Yeah.
There were definitely quite a few surprises.
Okay. Awesome. The next question is for Zainab. So preparation is a big part of New Year's Eve. How does the team go about predicting how much traffic to expect on the big day?
Oh, okay. So there is a lot of data science magic, I think, that goes into it. But I think maybe there's like a few key things I can point out. So obviously it's a very data-oriented decision. We are looking at, number one, how have past New Year's Eves been? So, what kind of spike did we get? What did we actually think we would get? What was the delta, and what are the learnings there? So that's like the first thing. You're establishing your baseline. We are also going to look at regions. So I kind of tried pointing that out in my slides. One of my slides had a graph of like, hey, look at our peaks throughout the day. So you'll notice the different times of the day is a different region, and they all have different spikes. So like North America, like California, PST, like we're not super excited about New Year's Eve. But if you look at like the Eastern Asia, super excited about New Year's Eve. So we'll take that into consideration. We'll take into consideration the regions that are coming in. We are also going to maybe consider world events. Like, do we expect an impact on New Year's Eve? Like, let's think back very recently, we think back to COVID, right? How do we think that's going to impact New Year's Eve? What, we have to make a call. So how are we going to speculate? And we're going to add buffers everywhere just in case we're wrong.
Got it. Thank you. I think we have 1 more minute left. Maybe I can squeeze in one more question. What is the SLA for the services, and how do you measure SLA and hitting reliability and availability requirement? This question is for the floor.
I don't think I can give a quick 20-second. So everyone here basically works on different services, and every service is going to have a different SLA. And even the question of like, what is the SLA and what should the SLA be is such an in-depth conversation with your customers. All of our customers might be similar because we are, I suppose, serving all of Facebook, all of Instagram, etc. But yeah, so there's no one SLA. Every service will have their own thing. An example SLA that I could talk about is in the Lambda service in UMA, I mentioned, hey, we have a scheduler. A very clear SLA that we're going to have on the scheduler is scheduling latency, right? So what is like the P99 latency that we're okay with, that we are promising our customers, especially knowing that we are serving user blocking traffic. Again, everyone here works and is expert on different services. If you guys want to jump in.
I think another one, like Zainab mentioned, it's all service dependent. Another one that's closer to products is what is the success rate of publishing? So if you have 100 uploads coming in, like how many of them actually go through and successfully have their encodings and thumbnails extracted and published. Another one is upload latency. Then there is, like Monish mentioned earlier, like there are the playback quality SLAs, like what's the average quality score that you observe in a certain playback session and so on. I think Zena put it really well. It's very service dependent, and it's not just one single metric. It really depends on the service, and it's the aggregate of all of these metrics that helps us define what the system should be doing at any given point.
Yeah, that makes sense. I think we've hit the end of our Q&A. Thank you guys for taking the time to teach us about video at scale at Meta. And we have a next round of talks and then a next round of Q&A. So I invite everyone to keep leaving questions in the forum. We really enjoy interacting with you guys and answering them. Thank you, everyone, again.
Thanks, Tia.
Welcome back from the
Thanks,
Q&A
Tia.
session. I hope it was entertaining. Till now, we focused on backend processing and delivery infra. Let's change our focus from the backend to the devices. While backends can be centrally managed, devices are closest to the consumers and make or break the experience. Our next speaker is Denise Noyes, who will tell us the story from the networking and players perspective. Denise is an engineer at Meta, leading improvements in video playback, quality of experience, and playback performance. Over to you, Denise.
Hey everyone, my name is Denise. I'm an engineer at Meta working on our video quality of experience team in video infrastructure. I'm here today to hopefully give a quality talk on video quality metrics and how we use these metrics to drive better quality of experience outcomes on our services. Most engineers recognize the value of metrics to understand the health of their service and hopefully detect anomalies. But what I'll talk about today is how we also leverage these metrics to make better real-time production experience that should hopefully lead to a better quality of experience when watching videos on Facebook and Instagram. So as an engineer on the video quality of experience team, we're responsible for making sure that your videos don't look like the one on the left, overly pixelated with scaling artifacts. We also want to make sure that you don't have to sit through overly long spinners waiting for your video to start, or see spinners when you're just getting to the best part in the video. There are also times that we've had to step up and manage our data usage. As an example, in the early days of the COVID lockdown, as you might remember, everyone had to switch to online, to work, for school, for their entertainment needs, and this put a lot of load on networks around the world. So we had to do our part to reduce at least the traffic coming from video streaming and achieve the right balance for users. So what do these problems of video quality of experience and managing traffic have in common? It's about balance. So again, we want to make sure that we balance having good quality without stalling and while using a reasonable amount of data. And sometimes this involves trade-offs. So for example, you can play the highest quality possible, but you might have a higher risk of stalls, or you might use more data, or you can minimize your chances of stalling and you might get potato quality or something that's overly pixelated. So to make these trade-offs, we really need to have a good way to measure all of the things involved. So the stalls, the quality, the data usage, and also the video quality so that we can make the best optimized decision. Today, I'll take you through our video quality metrics and talk about a couple of applications, both in how we enforce quality limits on cellular networks and how we use these quality scores in our adaptive streaming algorithms, and touch upon some future work in this area. So let's get started with our video quality metrics. So to start with, we need a way to predict how a human would perceive a video on our system. Ultimately, get everyone in a lab, rate everything on a scale of 1 to 5. Doesn't really work when you are operating with billions of videos. So we need a metric that will predict this quality score. So traditionally what we've had is an SSIM-based metric to measure in a full reference way the difference between the quality of the video that gets uploaded to our system and then what the user actually sees. So let's start, a user has a video on their phone. They might capture it inside the app or just capture it normally on their device, and they need to upload it to our service. Many times this involves transcoding the video to a lower file size on the device even before it's uploaded. From there, we ingest the video into our system, and we need to encode a full ABR ladder, potentially many in different codecs. And again, using different quality presets, different resolutions, we end up with multiple encodings to choose from. Then on the client has to decide based on network conditions, device settings, say the amount of data already buffered, what's the best quality to play at any given point in time. And finally, this video might be viewed under different circumstances. So for example, auto playing in feed, full screen and horizontal landscape consumption, or maybe even on a large screen like a laptop or a connected TV. And we know that if we look at the difference between what was ingested and what we actually played in a given viewport, this is how we compute what our quality score is. So again, to start with, we had an SSIM-based FBMOS score that served us pretty well. However, we started to see some limitations of the system. Again, in general, if the score was going up, we knew that quality was getting better. But we found that there were specific examples of video that we were overly penalizing. So this video of this tree, for example, left is the original, right is what we encoded as one of our lower bitrate encodings. The one on the right is degraded. It doesn't have quite as much detail, but it has an FBMOS score of 8. And to be honest, I don't think it's quite as garbage as the score makes it seem. Like, it's still pretty watchable. But we've seen that SSIM will overly fixate on a lot of details that might not be quite as salient to the average human who's actually watching this video. And we wanted a way to deal with this. So next we looked at having a VMAF-based solution. So VMAF is, again, another perceptual visual quality metric that's well used in industry. And it's great. It has much better accuracy than our SSIM-based solution. But the trade-off is it also consumes a lot more compute. And again, at our scale, with the number of different videos we have uploaded every day, we just can't afford to use all of this compute on every single video to achieve a more accurate metric. So we had some decisions to make. We wanted to use this, but we had to make it more scalable. So the first thing we did, not all videos are VMAF eligible. So for example, a creator uploads a video that we predict will get hundreds of millions of views. Yes, we can spend a little bit more compute to get a more accurate score. I upload a video that maybe might only be seen by my closest friends and family, probably not VMAF worthy. So we make some decisions based off of that. I mean, again, we still have SSIM. We don't have nothing, but we understand its accuracy will be more limited. Additionally, we see how can we actually make VMAF faster. So we leverage techniques such as better frame subsampling to speed up the compute of VMAF. We're continuing to evolve our outlook on this. So for example, we've done some work with UT Austin on Funky. And this, again, will have multiple operating presets, really evaluating the trade-offs between metrics accuracy and compute costs. So we have some papers published on this. So at this point, we have a quality score on a scale of 0 to 100, representing how good we think the content looks. But rather than just this continuous scale, we also really want to quantize this into discrete buckets. We don't think that human perception will necessarily perceive the difference the same at all points in the scale. So this is based on work that we've done with the University of Nantes to really understand the acceptance annoyance. So we think that there's, again, a certain quality level that if you go below it, the video is just not acceptable. Like, you've all seen kind of like pixelated garbage videos and you don't want to watch them. They don't look good. We don't want to serve them. We want to avoid being in that bucket. Then you might have, it's kind of annoying. You'll watch it, like if you care enough about the story, if you care enough about the content, but you're not going to love it. It's going to be notable. And again, like, we'd prefer not to serve that. Sometimes the network is just very limited and you have no choice, but we really would prefer not to be in that bucket either. And finally, you have not annoying. So again, it's not to say that there's no difference, no notable difference once you're in the not annoying bucket, but you would see that it satisfies the goal. It satisfies the goal of what you're trying to do with that video. And this is really the point that we want to be operating in. We've also done work that shows that, again, that perception of which bucket you're in depends on the context. So one case that we've looked at, again, with the University of Nantes, is how does the user's perception of quality, how is it influenced by device constraints? For example, if we prime you to think that you're almost out of battery, or if you think that you might be running low on your data plan. And what we saw is that users were actually a little bit more willing to accept lower quality when they had these device resource constraints. So let's recap where we are. So we have, again, a better compute scalable score on a scale of 0 to 100, ideally VMAF when possible. And we also have an understanding of where these inflection points are with our acceptance annoyance scale. At this point, I want to start talking about how we actually use these scores to make better decisions. One application is how we think about limiting quality on cellular networks. So we might want to do this because of data costs, or in cases like we talked about with COVID lockdowns. And we need a solution that scales across an array of diverse content, everything from reels to premium content to like live streaming of gaming, and ensure that we maintain a good minimum quality bar across our experience. So there are different ways you can do this. Traditionally, maybe it would be done by resolution, like we support HD quality or we support DVD quality everywhere. Or bitrate, like maybe we don't allow anything above 2 megabits per second or 1 megabit per second. But what we really wanted to see is like, how can we do this in a quality aware way? So just like I think it's pretty well accepted that constant quality encoding is better than constant bitrate encoding, we wanted to bring a similar concept to the way that we looked at cellular data limits. As an example, this is showing on the x-axis a quality score, a y-axis the distribution percentage of samples at each quality score for video encodings 400 kilobits per second using VP9 encoding. What this shows is that 400 kilobits per second of VP9 does not really tell you anything interesting about the quality in general. Again, you have some samples that have a quality score of 90, you have some that have a quality score of 40. So the bitrate itself is not a clear indicator of quality. This can also be seen on this graph. So here on the x-axis now, you have bitrate, on the y-axis you have quality. So let's say the blue line is one video, the orange line is another video. Each of these dots represents a given encoding with a given bitrate and a given quality score. And let's say, for example, you decided to draw a line at 500 kilobits per second. You can see that's fine for the orange video. Maybe it's very simple. Maybe it's using more advanced encoding like AV1, whereas say the blue video has a lot more complexity or maybe is using H.264. But that orange video, you would actually get a pretty acceptable quality in the 85 range. Whereas that blue video, 500 kilobits per second, you'd be stuck with something under 40. Okay, so hopefully I've convinced you quality is the way to go. So if we do quality limits, how do we actually define these MOS-based limits? What we want is a maximum quality score. So basically, do not exceed this limit. We want to make sure, though, that we still maintain a minimum quality bar, so at least one lane above a specific level. And just told you how bit rates were useless. They're not completely. They do make good guardrails. So we still have minimum and maximum quality bars that we enforce based on bit rate, just to kind of make sure that we're not doing anything too crazy. And finally, we also want some flexibility that we might be able to make different decisions depending on factors and contexts, such as, is this an intentional viewing situation? Or is this something maybe that's autoplaying that the user hasn't committed to yet and making different decisions based off of that? So let's go back to some graphs. So again, x-axis is bitrate, y-axis is quality. Each of these different colors, so the purple, teal, fuchsia, represents a different video, and each of these dots is a different encoding. So if we want to define these MOS-aware avoid on-cell rules, first we have this horizontal line, which is the maximum MOS. This is our do not exceed, don't play qualities above this line. For simplicity, I removed the minimum MOS. But we also have these vertical lines representing our minimum and maximum bit rates that we want to use. The minimum bit rate might be again, it's not really visible in this example. Let's say the video is like super simple, and even at like 300 kilobits per second, the quality is amazing. You know what? It's below the minimum. It's fine. Allow it. On the other hand, the maximum, again, this especially helps when maybe our accuracy is a little bit lower for some of our SSIM based rules. But it might say like, okay, we'll give you up into, in this example, say like 1.6 Mbps. If that's not enough to achieve your quality goals, we're stopping there. So we're still going to have some bitrate cutoff to make sure that, again, the bitrate isn't too high. So what you see, again, using these thresholds, again, for these 3 different videos that have different characteristics, again, maybe the complexity is different, maybe the encoding is different, we're still able to kind of enforce a uniform user experience. Again, they have relatively similar quality scores, even if there's a little bit of variance in the bitrate. And again, this avoid on cells doesn't tell you what you have to play. It's just a ceiling. So if your network conditions aren't great, you still might have something lower, but this is the ceiling that you would play. So let's recap. What are the benefits of this MOS-based avoid on cell system? So we maintain a consistent user experience. We also reduce the incidences of just playing really terrible quality because we don't understand that, hey, this is a video where we might just need a little bit more bits to achieve good quality. We can deliver at or better equivalent data savings as something based on bitrate or resolution. And it really allows us to optimize our usage on metered connections. Next, I'm going to pivot and talk about how we use quality scores in our adaptive streaming ABR algorithms. So a long time ago, there are times where we wanted to, for example, introduce lower bitrate lanes to really accommodate users who might be on more limited networks. And what we would see is we would introduce these low bitrate lanes, and all of a sudden we would see users using it too much, having negative experiences, and ultimately using our service less. And this isn't something that we want. Again, we really want to balance, again, the risk of stalls with the benefit of higher quality. So what we decided to do is really make the video quality of each selection an option in our algorithm. So again, to recap how the ABR algorithm works, you as input are given a dash manifest with a bunch of different qualities to choose from, each with different quality scores, different bit rates, different URLs to use. You also are looking at how much data do you have buffered, and what is your network conditions, what's your bandwidth estimate, and given all of those factors, the player has to decide which one do I use next. What we realized is that the trade-off between the quality and the risk of stalls is not uniform across all of these lanes. So I'm going to switch back to some graphs to walk through some examples here. Let's go back to our orange, I call it orange before, and our blue videos. So again, what we see is that to the left of this graph, every bit that you allow basically gives you a much higher gain in terms of quality score. So if we were looking at this, you see on this blue video, we actually have some lanes that would have a quality score of 15 or 20. That's not great. We would prefer not to serve those unless you really, really need to, because your internet connection is just not able to support anything higher. So at this point, we'd be willing to take a little bit more risk of stalling, be willing to wait a little bit more time for the video to start to make sure that you're at an acceptable quality, maybe even a little annoying, but at least not in that unacceptable bucket. So we're willing to take a little bit more risk on stalls. On the other hand, let's look to the right of this graph. You've noticed the slope of these curves flattens out quite a bit. Let's say for this video, again, the dots that are second to the right, quality scores are pretty acceptable. Hopefully, we don't think they're very annoying. It still can be improved. Like the one all the way to the right is probably going to look better. And it's what we would prefer to serve if we could support it. But it's not worth risking a stall to achieve it. Again, you have gigabit internet, 100 megabit per second bandwidth estimate, like go for it. You're probably fine. But if we think that there's a chance of stalling, we're better off like not taking that risk and play the quality lane that we know is good enough. So this is how we factor the quality scores into our decision-making in ABR in a way that we think really leads to a better trade-off between visual quality and stalls. With my last few minutes, I just want to kind of touch upon some additional future work in this area. So the first thing you might remember, if you remember my complicated diagram from many slides back, we look at the quality score as a difference between what we ingested and what we played. But we don't necessarily only get to ingest like pristine studio quality content. People like to upload videos that like maybe has been forwarded around the internet a number of times, like sent to multiple WhatsApp groups and downloaded, gone through multiple generations of like transcoding loss, and then finally uploaded to our system. So we really also need to augment this with no reference metrics to really get a better understanding of what the user is seeing. No reference metrics are harder. It's an area of academic research. It's something that we're participating in. So we know that there's a challenge, but we would really like to incorporate more no reference metrics into our algorithms. Another avenue that we're really pushing quality for is HDR. We know that it makes our content a lot more vibrant, and we're really proud to be able to support that across Facebook and Instagram. It also comes with its own challenges of how to measure quality and how we take that additional vibrancy into account. So again, this is an area of active research and something that we're continuing to iterate on. And then finally, I mentioned that we're really trying to balance the compute costs of visual quality metrics with its accuracy. So Funky Plus, again, these are all additional projects that we're continuing to invest in to really find the right balance that works for a service such as ours that hosts a lot of user-generated content. So thank you for all of your time today. I will stick around for questions. Feel free to reach out, and hopefully you learned a little bit, and let me know what you think.
Great presentation, Denise. I learned so much about networking and playback. The last presentation of the day is from Murli Babu. Murli is a senior director at Ittiam Systems, where he leads the Advanced Video and Research Unit. His work focuses on developing video, imaging, computer vision, and machine learning-based systems. He will show us how data drives some of the nuanced decisions when it comes to optimizing end-to-end media experience. After we hear from Murli, Tia will take over for another live Q&A session before we wrap up the event for the day. Now, let's welcome Murli Babu. Over to you, Murli.
Hi, I'm Murli Babu Muthukrishnan from Ittiam Systems. I'm going to be talking about influencing end-user media experience via device insights and analytics at scale. So we look at how you can bring new media experience to markets, and we'll also understand what are the characteristics and complexities of markets, especially the fast-growing markets. And we'll look at what device insight means and what we can do in terms of the analytics at scale. We'll also talk about some of the current status and future work that's possible. So understanding the media experience, bringing media experience to market, if you look at any service provider, let's say like Meta, the ultimate goal for them is to provide engaging, crisp, and very high quality content that captures the attention of the audience. Now, the content, engaging content really depends on the content itself. But that apart, user engagement can be enabled through very high quality video, right? How good your video quality is also determines the user attention. So that can be done in many ways. One of them is to have a very high resolution video, which can be very engaging, or you have a high frame rate video when you're looking at, let's say, sports content or a fast moving content, or you can even look at higher bitrate, which can give you a sharpness, crispness to the video. And not just that, we can also bring new features through leveraging the newer compression standard. Features like HDR, the high dynamic range, or AR/VR experience with depth map and things like that. Or you may want to even bring film grain noise, where you can get that old film kind of feel to your videos. And of course, there are also other techniques by which you can build, you can bring in an inbuilt scaling experience into the standard, by which you can get the adaptive bitrate kind of experience. So in summary, the goal is to provide very good engaging visual quality through, say, let's say like a newer standard like AV1, and with very minimal or no impact in the battery life. The user wants to enjoy the video, of course, not with the draining of the battery. So now, if you look at this whole video delivery chain, all the way from a service provider like Meta to the end user, we have four different players in this space. One is the service provider like Meta, who wants to provide engaging user experience, thereby increase their user base, and they want to do this in a very cost-effective way. Then there are these mobile chipsets. These are the chipsets which enable you to run a lot of your AV capabilities. They are provided by people like Qualcomm, MediaTek, Exynos, from Samsung and iSilicon. Right? They look at optimizing their chip design and the area, chip cost in the area. Right? And they also want to make sure that whenever they do something in hardware, it stays for a long time in the market, right? So that they can get maximum return out of the investment. And of course, they also want to make sure these hardware codecs stay for a long time. And then there's also a proliferation time. It takes for some time for the codecs to kind of become popular in the market. Right? Now, the key problem here is that there is a kind of a deadlock between the service provider and the chipset vendor. The chipset vendor would not bring any new feature unless they are very sure that the service providers are going to use it. And the service providers will not be able to bring the new features if it is not available in the hardware. On the other end of the spectrum, we also have the mobile OEMs who are going to use these chipsets and build the end devices. They are looking at how quickly they can bring good features, new features to the market. And because of the diversity that's there in the market, they will also end up creating many variants so that they can cater to the large audience. And for them, enabling new codecs or new features is very key to be able to get new customers. At the other end of the spectrum, we have the end users who want to have better visual experience, and that's what service providers are targeting. And they want to achieve that better experience by having very minimal impact on the battery life. And of course, they also want to ensure that whenever they buy a device, it stays with them for a longer time so that they don't have to spend again and again. So one way to be able to bring new experience, new features, is to look at the software route and not necessarily go the hardware route. So this is where understanding the market and understanding what kind of devices are there in the market really helps. So before we go into the device insights, we look at what the characteristics of the markets are, and we'll pick some of the emerging markets. So this study was done by us for Meta, especially the Meta's video infra team. So we looked at some of the fast and emerging markets, fast growing and emerging markets like India, Brazil, China, right? And we picked one market, the Indian market. The Indian market has a lot of complexities in terms of the device variants that are available. The market in India is huge, several 100 million users. So there are different operating points or the price points that are available so that they can cater to, the device OEMs can cater to the whole market. And then they want to create different SKUs because of this so that they can look at different segments of the market. And these SKUs actually create one other complexity, that is they come with different operating points in terms of the performance, let's say the codec profiles or the screen resolutions, and whether they have an hardware codec support or a software codec support and things like that. So understanding a diverse market or a fast-growing diverse market like India, you need to understand the media capabilities, and that can only be done through creating a lot of insights through device analytics. So a little bit more about what the complexities that we are faced with when we study such a market and try to understand what we can bring as new features into the market. You can see that even though 70 to 80% of the devices are less than 3 years old in the market, there are also devices which are more than 4 or 5 years old. So you are looking at a spectrum of devices which have been released in the last 5 years. So you need to make sure that whatever you do, you support those devices. This study was, of course, performed in 2020, 2021. So we looked at in 2020, 2021, there are devices which are released in 2015 which are still active with the users. And then in the emerging markets like India, there are many brands which make the market size. It's unlike the markets you will see in the US or in Europe, where there is domination by one or two brands, 60% domination by one brand and 20-30% by the other two brands. That's not the case here. You're looking at like 15 different brands which are very active. And if you're looking at the Android ecosystem, then because of the 5 years of the lifespan that is there with these devices, different vendors, different OEMs, you're looking at different versions of Androids being run. So when we did the study in 2020, 2021, there were 13 plus Android versions that were active. And then you also have different screen resolutions that are available in this market, right? So if you want to bring a very good quality video experience, you have to bring this at different screen resolutions. And then, of course, there are different chipset vendors that are making up this market. So you need to see how to target these different chipsets. So we look at how you want to do device insights to be able to get a grasp of this market, understand the market better, and see how you can bring your features or your upgrades to the market in a way by which you can cover the entire market. So as we looked at the market in the previous slides, device fragmentation is one of the key characteristics that we need to study. We need to look at the device fragmentation. Device fragmentation also leads to the different hardware capabilities. So we need to understand what the hardware capabilities of all these devices are. There is also software capability that varies across these devices. So you need to understand the software capabilities. And they also have different AV capabilities. We looked at how they can have different codec profiles or different codec formats being supported and things like that. So you need to understand what the AV capabilities, the audio video capabilities of these devices are. And look at the overall performance and see what kind of performance you can bring by doing an analytics. So in summary, device insights can help you get the key data points that can help you bring new features and also time your upgrades for the features. And because the complexity is involved in this market in terms of the various parameters that we talked about, you need to do really at scale analytics here. That's the one which will help you determine what is one or two good operating sweet spots that you want to have for your service. So we look at how you can develop insights by looking at all these analytics parameters and how you can do analytics at scale. So as we talked about, there are multiple brands that are there in the market. You need to understand what these brands are. You need to look at the years of release, the Android versions. And you also need to categorize them into mid, high, and low tiers to understand where you want to really bring your feature, whether you want to bring it to the high end, the low end, or the mid tier range. Then, as we talked about, there are many chipsets that are available, different screen resolutions, different battery capacities, especially when you're trying to bring some features in software. You need to be very, very conscious about the battery capacity, right? How much of battery drain is going to happen. And today, if you look at most of the mobile devices, they all have some kind of an ARM core in them. So you need to look at what the ARM architecture is, right? Because that helps you understand what kind of features you can bring. So consequently, the ARM CPU frequency, what frequency can you run? How many cores are there? Because if you want to run a software codec or you want to run a software feature, you need to look at how many cores, how much of processing capacity is there. You also want to look at what is the per core processing capacity of the ARM, because even though you have multiple cores, you may want to run your feature only on a few cores so that the application is having enough room to be able to run on other cores. So if you look at this gamut of characteristics, you need to analyze all of these to be able to arrive at an operating point, the optimal operating point for a service provider. What is the right resolution that you want to pick? What is the right frame rate you want to pick? What is the right bit rate you want to pick? And of course, the coding tools and also the profiles that you want to support. All of this is only possible when you can do large data analytics of the parameters. So one such study that we did for Meta was to look at what would it take to be able to bring a new standard like an AV1 in software on the devices. By doing this, you can actually provide better video quality and of course, consequently, better user engagement. So we picked 61 devices, which were a representative set of the entire market. They were categorized into 30 high-end devices, 14 of the mid-range, and 17 of the low-end. And different screen resolutions were part of this mix. And about 50 devices were having the latest ARM v8 architecture, and 10 devices were from the ARM v7. Of course, there are 15 brands that we talked about and several different Android versions. The high, mid, and low category was categorized based on the ARM architecture, whether it was v8 or v7, and also what kind of ARM core was there. Is it A7 and A55X plus? Then it is called high end. If the A53 that was there was having a clock frequency of more than 1.8 gigahertz, it was called the mid tier, and anything less than that was called the low tier. And of course, the v7 architecture. So we also looked at what kind of tests we need to do to analyze and what kind of data we need to gather. One was to look at the real-time capability of these devices, real-time analysis, playback analysis. So you want to see whether the video plays in real time. When you say real time, it should have no frame drops, no frame skips, right? And it was considered as passing real time test if it was dropping less than 2% of the frames that were available. And also we wanted to look at the CPU usage. CPU usage in terms of how much is the software is loading up the CPU, and what is the CPU available for the other task. So the average value taken of the CPU usage is used as the final measure for this. And the other one we did also was to look at the battery usage, right? How many hours of playback was possible with this software coding. So we looked at 5 different resolutions: 270p, 360, 540, 720, and 1080. 2 different frame rates, different bit rates through the QP points, the operating QP points. And then we also looked at 2 different configurations of the AV1 software itself, especially the SVT AV1 software, which had one particular feature called the tools of, which enabled the decoder to have lesser complexity compared to the other case of the tools of. So we are really looking at big combinatorial tests here: 5 cross 2 cross 9 cross 20 data points, about almost 1800 test points. So you need to have these many test points to be able to see what would be the behavior of software or the feature that you're trying to bring. Let's say the software AV1 codec, when you run this decoder across different devices. So the setup that we had for analyzing this was to have the mobiles connected either through a USB hub or the PCIe to a PC, and all the tests were launched from the PC into the mobile device as if it's like downloaded and played. And then we are collecting all the log information, logging all the information to be able to do analytics either on the device or on the cloud. We also, because these are all very valuable data points that we are generating here, to be able to understand the market, to see what kind of tests can be performed, to understand what features are possible, you need to make sure that all of this data is well protected. So we had a centralized server through the firewall, enabling a lot of data protection using a separate network. Hosts were secured with the DLP, the systems are protected with the Symantec endpoints, and we had the automated system backup. So it was a very secure and safe environment by which we are collecting this data. Now I'll play a small video to be able to understand how these tests are done online. Yeah, so you have an interface by which you can log in and look at the devices that are available. So at the time of recording this video, we had about 40 devices connected across 2 different geographies. And then you can go and select what kind of device you want to, the group you want to pick. And then you have 4 devices connected to this group, and you can go and pick one device and look at it. So remotely you can access the shell to be able to run some of the commands. And of course, you can also see the video being played there. So the video which is being played, and a lot of information is being collected about this video as it plays, right, in terms of what we talked about, the real-time playback capacity, what is the battery drain capacity, and what is the CPU usage and things like that. So this kind of gives you a very nice and easy interface by which you can run your tests and collect the data. So different clips are played in a loop back to be able to look at the characteristics. Right? One sample analytics is what I'm showing on the screen now. So we can see that there are about 46 devices which were able to do 1080p 30 in real time. Right? So, of course, the aim of this presentation is not to talk about the results, because that's a separate topic by itself. But the idea is to show how through these kind of device analytics we can arrive at some of the results. So as I mentioned, we looked at different frame rates for 60 FPS. We have different characteristics that we are seeing, that for 540p, almost 52 devices are able to play 540p 60 in real time, and whereas when you go to 1080p 60, it's only 23 devices that are able to play that. And if you look at 720p 30 itself, all the devices are able to play. So that's probably an operating sweet spot. And 1080p 30, there are only 50 odd devices that are able to do 1080p 30 in real time. We also studied the battery capacity. So if you look at it for a 720p 60 playback, the average battery capacity was like you can do 11.5 hours of playback, and for 1080p 60 it was about 8 hours of playback time at a battery capacity of 4000 mAh. So we also did another analysis where we wanted to study what kind of codecs are available either in the hardware and software on these devices. So we picked about 300 devices to understand this, because this covers the entire or a large part of the world market, right? So what we found was that through these analytics, that AVC, the S.264 standard, is prevalent in hardware, and it supports 720p 60 and all lower ones. And almost all devices support AVC hardware playback. HEVC was having 95% market penetration of the devices that we looked at. And VP9 hardware penetration was about 70% in the market. As I said, some of these analytics that we have done and the results of these analysis have been published in other conferences and forums, one at SPIE, and also there is a Meta blog which talks about how the AV1 software codec was analyzed and what were the results of it. So as I said, the focus of this talk is not talk about the results, but to talk about the framework and the setup and how you want to go about doing analytics to be able to arrive at the operating sweet spots, the profiles that you want to support, what features you want to bring on your platform. We look at some of the current status. The current status is that we have about 480 plus devices in the lab, through which you can do a wide range of market study, whether it is India market or some other market or even the world market. You can do a large study of all these devices. And we continue to do a lot of continuous analytics. If you want to bring new features, if you want to bring new upgrades, a continuous study, continuous analysis of the market should be done. This is one example of how we continue to upgrade the device analytics, the lab as well as the framework, to be able to do more and more analytics. I talked about how we did initial analysis with 300 devices, then we did another analysis with 60 devices. After that, we also added 170 more devices. That's where you see the number close to 480, which was used to, along with 130 devices from the previous set, was used to study what is the behavior of hardware codecs, especially when it comes to real-time communication like a video conferencing or things like that. So we looked at hardware codec stability in terms of memory leaks, their performance. Also looked at what kind of bitrate deviations that are there. You say you want to encode a 2 Mbps, is it within 2 Mbps or is it 2.5 Mbps? That kind of analysis we do. We also looked at what is the encoder compression performance compared to, let's say, a software codec. How good was the encoding capability of the hardware encoder compared to the software encoder? And we also looked at the latencies and time and the initial decoder delays, because that kind of is very important in a real-time communication scenario. So in all, we have done a lot of study, continuous study, and having this kind of a setup and a framework has really enabled us to be able to do this study and arrive at the key decisions that will help you guide to bring new features, new software, new capabilities into your service. Right? there is a lot more scope we can do with this kind of a setup. You can understand device fragmentation in a continuous way. You can also understand how the user experiences in terms of whether there's buffering, caching happening, how is the delivery happening, or you can even look at, if you want to bring some new features, let's say like a HDR, you can really go and study how many of these devices are supporting HDR and how many of them are not supporting, and what does it take to even bring such a support on the software. And then this also gives you a lot of feedback for you to be able to understand what kind of infra I should have and what kind of ROI can I have on this infra and what kind of efficiencies I can expect out of this infra. So it kind of gives you feedback on what encoding recipes you should operate, what transcoding recipes you should operate, so that you can get the best out of your infrastructure, and also you give the best to the user in terms of the user engagement. So in summary, these data insights and analytics can be done for any decoder characterization, encoder characterization, or even the hardware software partitioning and characterization. So we can look at multiple standards and also look at what kind of playback capabilities are there, what kind of CPU load does it have, what impact does it have on the battery, and look at what kind of upgrades you can bring. As I talked about, we can also look at what kind of special features that you can add to your service by looking at the specialized services or features like HDR and higher frame rates. And you can also do some very focused study in terms of how the proprietary or open source components are behaving on a device. And of course, the framework is set up to do analytics at scale. And as I showed in the video that was played, it's a web-hosted interactive service that can enable you to do a lot more analytics and data gathering. Thank you.
Hi, everyone. Welcome to the second round of Q&A for day one at Video at Scale. I have Murali from Ittiam Systems and Denise from Meta with us to answer the questions that you guys have for their talks. Thank you for your talks. I think it was really cool learning about how video playback works for videos at scale. I think we have a bunch of really good questions, so I'm just going to jump right into them. The first question is for Denise, and the question goes, are the quality and bit rate limits achieved using KEP CRF encoding, or do you employ some content adaptive encoding?
Hey, well, thanks for the great question. So first caveat, so my expertise is more on the playback side, but work really closely with our partners on our encoding and processing teams. So especially for our more advanced encoding families, like for VP9 or AV1, we actually rely on a lot of pre-processing and optimizations to build out like an optimized convex hull. So what this pre-processing does is at different encoding settings, different resolutions, we'll kind of be able to assemble that final convex hull, and then the output would be a CRF we would end up using for each encoding in the ladder. But it is very content dependent, and it's not, we don't have like a fixed bit rate or a fixed CRF that every single encoding lane in the AVR ladder would get ahead of time.
Got it. Cool. The next question is also for you. So why only 3 subjective buckets? Why not, for example, standard 5 buckets, having excellent, good, fair, poor, bad? Or is there any specific production or practical values to having 3 buckets?
So I think the important nuance here is really kind of the differentiation and the distinction between MOS and acceptance annoyance. So what the acceptance annoyance 3-bucket model is really giving you is, in a specific context, is this MOS scale viewed at, or is a specific MOS score or quality score acceptable or not? And the thesis is that in different contexts, for example, a MOS score of 2 may be unacceptable, or it may be, maybe it's a MOS score of 3. So as an example, this isn't really relevant to Meta per se, but there's been prior research in the space that shows the amount that you pay for a streaming service may impact your expectations about what quality is good enough. So the more you pay for a service, the higher your expectations would be about quality. And more in our case, for example, I think you talked about kind of your data budget might be a factor if you're watching on Wi-Fi or cell. If your battery is about to run out, if you're low battery, you might be more acceptable or more accepting of a low MOS score. So it's really trying to overlay this acceptance annoyance scale on top of MOS rather than only looking at MOS and trying to understand which factors are most salient in making that decision.
So does the buckets shift based on like what app the video is being played in?
I think there's a lot that we're still learning in the space. So we're trying to understand what are the factors that might be might come into play, and how do we actually apply those in context to make the right decisions for our users.
Got it. Thank you. Murli, the next question is for you. How are the test cases and test points decided? Do we need to provide them, or can Ittiam design those?
Yeah, it really depends. For example, if the customer, or let's say in this case, Meta has very clear requirements, then we can take the test cases that are coming from the customer. If they have a very high level requirement and they say, okay, you go and decide what kind of bit rates have to be tested with, or what kind of features have to be tested with, then we can jump in and design the test cases. So it really depends on what the customer really wants. If they're very clear and they have their own test cases, then we could use them. Otherwise, we can define and design the test cases.
Got it. Yeah, flexibility is great. The next question for Denise. How do you address the conflict when the quality scores are the same for 2 different resolutions, but at the same ABR rung or representation? Do we serve the lower resolution or the higher one?
This is a good question. I want to make sure, hopefully I get the intent of this question correct. If not, let me know in the comments and I'll try to follow up. So generally the expectation is if the pre-processing convex hull model I described in the first question is working, we generally wouldn't expect the player to be provided with an ABR ladder that has multiple choices at the same quality. Like, we strive to have kind of good, just noticeable difference spacing between the lanes that we can choose. It's possible that if scaled down to perhaps a very small viewport, maybe the quality will saturate and there may not be quality gains from continuing to go up within that specific viewport. So if we did end up in a scenario where there were no meaningful quality gain from playing kind of a higher bitrate encoding to the user, we would default to using basically the quality lane at the lower bitrate that has the same quality score.
Got it. Awesome. The next question is from Murli. Was BD rate used to measure the compression gain? And if so, what quality metric was used for benchmarking?
Okay. So yes, typically BD rate would be the, I would say, a top pick for measuring the compression gains. Okay. But of course, we can also do some visual tests, and like what Dennis also mentioned, you can use just noticeable distortions and things like that. But yeah, BD rate would be a very top pick for objective metric that you can start with.
Got it. Awesome. The next question is also for you. So do we need to test for capabilities of different devices with the same chipset?
Yeah. So what we have found from our experience so far is that even though the chipsets are all the same, the OEMs, for different reasons, maybe they want to have a lower skew at a lower cost, so they really actually turn off some of the features. So even though the chipset is the same, the OEMs can switch off some of the features. So then you would not get those features available on those queues. So it is very important to do different tests, even though the chipsets are the same.
I see. So that's why you have so many different devices.
Yeah.
All right. The next question is for Denise. How does Beamr handle live videos where the bitrate and quality values of different lanes may not be available a priori?
It's another great question. So live comes with a whole host of unique and interesting challenges on top of video on demand, which is tricky enough to get right in some cases. So specifically around the quality and bit rates that could change, we don't necessarily always have the same real-time quality scores to make the right decisions. We do attempt to send the client kind of like a running average current bit rate for each of the ladders to make best guess decisions around kind of when to adjust up or down as needed based on the current network conditions and current buffer status. But it is it does come with its own challenges.
Got it. Makes sense. The next question is also for you. So how important are frequent quality switches in determining user experience? More concretely, do you see user engagement reduce when the quality fluctuates?
Yeah, there's a lot of factors that really go into the quality of experience. And it's, I think, a challenging area of research to really pin down how much any one factor matters. Like even with the quality, do you do the watch time weighted average across the entire video? Do you have some sort of like recency weighted bias where you look at the quality at the beginning of the video is the most important, or maybe it's the quality at the end that's the most salient? So I would say that this is far from a solved problem and definitely goes into this bucket of lots of opportunity for future work and future understanding. I would say that one thing we do monitor at least is at least tracking over time what the frequency of quality switching is in production. We've definitely seen that be a signal before where if it makes a sharp jump up or down, we need to at least take a closer look and make sure that we don't have some kind of unexpected bug in production, or understand like kind of what the cause of that is, because it could be indicative of a problem. I mean, I think all things being equal, like you definitely don't want it to oscillate back and forth. Like say that you had a choice between just using resolution to keep things easy, say like 360p, 720p, 1080p, like if you could just kept jumping back and forth between 360p and 1080p every 5 seconds versus staying at 720, like that would probably be annoying. So I think you definitely want to make sure that you don't have bugs there, but I think in terms of how exactly you model that into the quality score gets a little bit more complicated.
Got it. So is there active work at Meta right now to actually maybe figure that out more?
It's, I think, one of the areas and like one of these factors of what are the things that matter. I mean, there's also like how much does audio quality matter? We know that that's very salient to the overall quality of experience, but how do you weight the visual quality versus the audio quality? Does it matter for different content differently? I think there's a number of there's lots of room to kind of continue to improve this model and make it more holistic.
Makes sense. Thank you. The next question, I think, is from Murali, but Denise, feel free to chime in if you have anything to say. The question is, how is the per core utilization measured on the device while encoding, decoding, and processing?
Okay, yeah, I'll answer that. So the per core utilization is done based on how many threads you are running your particular software under test. You could be running them as a single core, or you could be running them as a 4-core or a 2-core. So based on how many cores or how many threads you are spawning, you can look at the per core utilization.
Got it. Thank you. The next question from Murali. Do you think there are other factors, maybe like temperature, that can affect phone performance? And how do we account for these in the experiments?
Okay, so all of our experiments are done under the normal room condition because that's how we want to that's how the video is going to be consumed, most likely, right? So most of our tests are done under the normal room conditions, temperatures. The only thing that we feel could affect the performance in terms of temperature is how much of clock speed the processor is able to sustain. That's the only thing I can think of. But typically, all our tests so far have been done under room conditions.
Got it. Thank you. The next question is for Denise. So I think you mentioned about non-reference original quality as like future steps or things that Meta is investing into right now. What are the additional challenges for understanding this?
It's a lot less of a solved problem in terms of what's the best way to really handle this content, to just take an input stream and kind of reduce it to a value of how good that quality is. I think there's a lot of interesting challenges also in kind of some of the new formats that we're seeing are really popular in short form video, where you really have like multiple layers of content. So for an example, you may have an original source video from a camera roll that was captured at 1080p and a high bit rate that looks very sharp, and then you have like a dancing Bill Hader sticker on top of it that's intentionally like a little bit lower res, and like how do you define what the composite score of that content is, or the inverse where you may have like a throwback clip from like a 90s commercial with then very sharp overlaid text on top of it. Again, how do you judge what that final quality is and kind of take it into account for what we present to the end user? So it's definitely something that we are interested in understanding more and doing some work here and trying to understand which features are most salient and most aligned with like user perception. But again, it's has a lot of interesting challenges, especially at scale of doing like the number of uploads a day that we handle.
Awesome. Thank you. The next question is also for you. Is there any work done to dynamically generate new bitrate or quality levels to give the best user experience?
That's a good question. So one thing that we do is not necessarily dynamically create new lanes on demand, but we do have a mechanism that, say, a video goes viral at some point after it's uploaded, where maybe based on the initial watch time predictions, it didn't seem like it may qualify for something like our AV1 encoding recipe, because we want to strike the right balance of making sure that we use our most like compute intensive codecs for the content that will get the most distribution. We do have a mechanism for like after the fact, if we detect that, oh, we didn't think this was going to get a lot of watch time, but actually it is really popular, we can then basically enqueue it for our more advanced encoding families. So something that does have a kind of marked shift in consumption patterns will get new encoding lanes in that way. But it's less of a case of, oh, we see that we only had a 360p lane and a 720p lane, and now we're going to like go and insert a 540p lane in the middle, or we're going to go and put like a 144p lane at the bottom.
Got it. Yeah, maybe like helping viral videos go more viral by sending better quality encodings. The next question is for Murli. What are the other areas apart from media where such end user device capabilities can be useful?
Yeah, so we now see that most of the devices, especially the mobile phones, are coming with AI-enabled features, right? So it will be good to study what these AI features can be used for in terms of video capabilities, whether it is encoding or decoding. So studying the AI-enabled features may be a good task to consider in the future.
Got it. Thank you. We have another question for Denise. So are there other factors worth considering when making playback choices? I guess this ties in line with what Murali was talking about, battery life, device temperature, maybe CPU consumption. Do we consider those as well?
Yeah, I mean, I think there's considerations that are made first in terms of like which codec is most appropriate to decode on this device and what the device capabilities are, if they can even decode certain content in the first place, and if so, at which resolutions. When trying to decide, well, do you allow perhaps like a lower resolution BP9 or a higher resolution H.264 stream that might not be like compressed as well. I think there are other factors that we're also continuing to understand. So then you might have the question of, okay, it's capable. It's not a question of just capability. Like it can decode, but which one is optimal? And there are some things to consider in terms of, I think, battery life and kind of client-side compute costs when you're evaluating, especially like hardware decoders versus software decoders and different options. So that's something that is being looked at.
Awesome. Thank you. I think we have time for maybe one more question. And the last question goes to Denise. So what are the challenges that you face when you try to launch a new quality metric?
Yeah, so you have an idea for a quality metric that is more accurate, but one of the challenges that you have is once you're actually relying on these metrics to make client-side decisions, it's not always as simple as we've done some research to prove that this one has higher predictive accuracy, ship it and move on. You definitely have to run production tests because it may have, it may impact the ecosystem in a way that you don't necessarily fully predict. So you want to be able to quantify that and measure that. This is especially challenging when you have metrics and when you have new metrics that might not be on the same exact scale as the old metrics, and you have different kind of numeric thresholds for making certain decisions. So it can be a more involved effort to make sure that we do this in a coordinated way across encoding and playback and delivery, and also monitor this real time to make sure that it has the desired kind of positive quality of experience on the end user that we expect.
Got it. Makes sense. Thank you. I think that's all the time we have for our Q&A. I want to thank Murali and Denise again for taking the time to teach us about things they're working on and answering our questions. Yeah, so I want to wrap things up. I think we have one more closing remarks by Shinjin, but after that, I think that marks the end of day one of Videos at Scale. Thank you, everyone.
Thank you all for joining us for day one of Video at Scale 2023. Don't forget to tune in tomorrow for day two. Tomorrow will feature presentations and Q&A sessions with speakers from Eluvio, Google, Heygen, and Meta. As a reminder, all videos from today will be posted on the AtScale conference webpage, the AtScale Facebook page, as well as the AtScale YouTube page in the next few days. Thank you and see you tomorrow.